A very good morning to one and all. So now we are on the third day of the course on fax devices and distributed generation. So we have with us our expert, Dr. YP Verma. He is assistant professor in the UIT Punjab University, Chandigarh. And he is going to deliver a lecture on inertial response for renewable energy sources. He is a very good expert in this area of power system, and I think you will be really gaining a lot from this. And we have one more session of him on GAMS also, so he will be delivering that. And he has a lot of papers in SCI journals. Even when I go and search in it, I've seen his papers popping up. So he has a lot of SCI papers in both elsewhere, Taylor and Francis. And he has also a number of funded projects. He's now also working with one of the funded projects and to his credit. So I just hand over the session to Dr. YP Verma.
Okay. Thank you very much, ma'am. Thank you for the nice introduction. Very good morning to one and all. Ma'am has already introduced that I've been working in the area of distributed generation. And the topic that I have picked up today is inertial response from renewable energy sources or distributed energy sources. Inertia is a very important term and very important factor for the secure and reliable operation of a power system. And particularly when we expect that renewables share is getting increased, there is a threat to the inertia. So it has become very important that renewable energy sources they also contribute towards the inertia of the system. Otherwise, system can collapse anytime, and we can observe frequent blackouts. So how do we make our renewable resources and DGs to contribute towards the inertia of the system? That is what is the talk of the day. Let's you know begin that we go to the background and then we'll come back to this. This is what is the scenario in India at present, and why I'm telling this around 15% at present out of the total generation that we have. It is going to increase, and this increase is going to be very significant, and it may be quite possible that by the year 2025 or 30 it can be one fourth of the total generation. And we are well aware that these sources they are intermittent in nature, they are stochastic in nature, and we cannot rely upon them. And if this is the amount of share that they have, then it can be a problem for the secure and stable operation of the power system. And particularly if you see among these renewables, the wind and solar, they are the major share, and they are highly intermittent. However, if you see in DGs, hydro is a very reliable one, small hydro, but its capacity is small, still it is being explored, and mostly it is in hilly areas only. Then we have biogas and all other resources, they are also being increased, but major share is from the wind and solar, which are highly intermittent. That is why this inertial response from these sources have become very important. This is what is the scenario, and that is what why we are going for this more of the generation. We have enough of the coal, but because of the restrictions on the emission, it has become mandatory for us that we go for the higher renewable energy sources. The per capita consumption in India is very low as compared to the world average. It is 2200 kilowatts. And if you see the developed countries, they are having very high per capita consumption. So if you want to be a developed country, we should be energy sufficient. That is why we are striving hard to achieve the target of generation from conventional as well as from the renewable sources, particularly renewable, because we want to have a sustainable solution for our energy problems. There are driving factors. You must have heard about the Kyoto Protocol, then Copenhagen Summit, or recently the Paris Summit. Now we are also signatory to that, and we are going for emission cut. There is by 2020 there is 2020 that we need to increase generation of renewables by 20%, reduce consumption by 20%. So this is how the policies are being made, and after some time certain emission allowances will be allocated and you cannot go beyond that. So only solution left with us is to increase the renewable energy sources. Emission trading schemes are also there. There will be the opportunity for renewable energy sources, particularly independent power producers, that they start participating in trading schemes and ultimately earn revenues. This is the biggest revolution that we have in India, Electricity Act 2003. It's a big document, but it has brought major changes in the power system operation. Few policies which I have listed out: renewable purchase obligation, RPO. You must have heard. This is what is a condition on each and every state, that they need to generate power from the renewable energy sources, particularly wind and solar, out of their total generation. And if they do not do that, they need to purchase it from any of the power producers which are generating from the renewable energy sources. So these are the policies being made which is enforcing that more of the renewable energy sources should come, and they should be used. Feed-in tariff. This tariff, particularly for solar and wind, it is being provided. Higher tariff is being provided so that you know they get their investment cost, and it is they are assured that they are going to get this return for the quite considerable amount of time, so that they are many of the investors, they come forward. Then we have renewable energy certificates. This is again a very important uh, factor. Here, these certificates are issued by some competent authority, and it is given to certain power producers which have a generation of up to 1 megawatt. And as a result of that, if any of the state who is not able to generate, meet their RPO, meet their obligation of 10% or 20% of renewable resources generation, they can purchase these renewable energy, from those power producers which are having these renewable energy certificates. So these sort of options are being provided for the independent power producers, which are encouraging the investment in renewable energy sources. Then generation is also made license free, so it is made open. So you can have your own PV panel at your home, and you can also have a small wind turbine. So you do not to have any license for that. That is what is the major driving factors which have led to the growth of renewable energy sources in India. Now, we got an area, the topic, that is the inertia. In before moving to this, we need to understand that how our system operates. In our system, we operate the total generation. It should be able to meet the load and the losses. And in case there is any change in any of the load, what happens initially? If you see that frequency which is 50 hertz, if load increases, frequency will go down. Why frequency goes down? Frequency goes down because the kinetic energy, rotor speed goes down. Rotor and speed is directly linked with the frequency. So frequency is going down, and the kinetic energy which is stored in the rotor, it is being released to supply that additional amount of electrical energy which is needed and which was there because of the load change. So what happens? The load change is, we can say it's a small signal stability issue, a small signal, but there are incidents like fault, and there can be outage of any line, outage of a generator, where there can be large amount of power variations. So under those conditions, how different generators should respond? See, if you see our conventional generators, what we are saying, grid connected with small renewable energy sources, it has sufficient inertia from conventional sources. Why? Because we have thermal, we have hydro, and they are rotating, they have kinetic energy stored. If load is less, obviously they will have higher kinetic energy stored, and they can release it as and when needed. Similarly, if there is higher load is increased, as a result of that, kinetic energy is released, speed slow down, okay, frequency varies, but any load amount of change, if we have sufficient amount of generation, so it is able to meet any load change, okay, without major change in the frequency. Yes, the response of these sources are slow. If we talk about the thermal, like to start generation, we do have spinning reserve, but still it needs some time to take up the generation. Like we need to open the valve, the steam has to be increased, and generation will start. So it and the response that we need from our sources is in starting from a few seconds, like 3 4 5 seconds, then 30 seconds, then minutes time. So we have primary reserves, secondary reserve, and tertiary reserves, which are time dependent. Whereas in conventional sources, they are no doubt able to supply it, but the time taken by them is slightly large. So they have sufficient inertia. And if there is small renewable resources, why I'm taking small renewable resources is because I told you renewable RES renewable resources are intermittent in nature. If there is, let us suppose, lesser amount of wind, which we are expecting, it is not available, or load also changes simultaneously. So impact is double. Sometimes it also complements, like you have more of generation of renewable resources and load also reduces, so they are complementing each other. Sometimes both of them are in one direction, sometimes they complement each other. But the problem is that conventional sources are slow in response, and in case we have significant amount of renewable interconnected, then it becomes a problem. Why it becomes a problem? For example, if we talk about a wind, which we are discussing, in wind we have mostly induction generators which are used, and induction generator itself needs reactive power to work. And in case there is, and wind power, I will discuss that, it works on a certain speed range only. And in case that speed is beyond that limits, cut in and cut out limit, then we need to cut it, stop the operation of the wind power. The supply which was coming from the wind power is now not no longer available, and the load we need to cut down, or maybe we need to supply some other generation. Now when we need to start it again what happens, that this wind generator, it will require power. So from where it will get the power? It will draw power from the existing sources only. So if it draws power from the existing source, it means it is acting as a load to that. So if the amount is small, so it is not going to be a big load. So whatever is the inertia available with the conventional, it is able to meet it. But if you see the second one, if there is the large amount of renewable resources, it may have, it may have, if renewable energy sources are properly coordinated. So that means that we will discuss later. It may or may not have. If amount is very large, sometimes we need to go for load shedding, and then we start generation. And there has been certain documented methods now, that how to start under these situations. Like if you have to go for the black start, when we have the blackout in India, how to restart the system. So there is a proper documented procedure for that, that this is the generator need to be started first, this is what is the second. So this is how they are connecting, and we are able to come up with this black start capability. In third condition, where we are, it is isolated, or a microgrid condition. And in microgrid, we expect major share is from the renewables like wind. It can be from maybe a gas plant, if it is available there, or the solar mostly. Sometimes fuel cell and all these things, they are being used to operate this microgrid or small isolated grid. And there is hardly any a system which is rotating in nature, just like your synchronous generator. It becomes a problem there, that in case there is a load change, who will take care of that, what to do in those conditions. And particularly when we have large amount of photovoltaic cell. See, we will focus on the two. One is wind, and second is the photovoltaic. In wind, we expect, because it's rotating in nature, wind also has a rotor. It means it is going to decrease or increase speed depending upon the load change. So it can contribute to inertia by its inherent nature. But what about photovoltaic? It doesn't have an inertia as such. But when we are targeting the capacity of generation, it is going to be very very large. So what in those conditions, if there is no solar, all of a sudden we never know that how this, though we have the prediction techniques, but solar energy may be available, it may not be available. And if major share of the this photovoltaic is yeah, power is not available, then how our system is going to operate? And if there is a load change, and if fault occurs under those conditions again it becomes a severe effect. So that is why there are research going on that how to make use of these photovoltaic system as well as the wind energy to support the inertia of the system. It has become a very very important issue, and particularly in microgrid areas, smart grid areas, uh, this virtual inertia term, which I will discuss now, it has come up now that we need to have inertia which is virtually available. It's not actually rotating, which we say, but it is virtually available. It can be provided. That is what is the major area, and there are latest paper which are coming, and there are lots of scope in this. Now, this is the term, this virtual inertia of photovoltaic. Let's focus on the photovoltaic first. What is the, this is what is the basic, smart supply demand imbalances. It changes the frequency. That's quite obvious, even if there is a photovoltaic. And the total system inertia, see, we can calculate in equivalent values. How much power is there by solar power? So if we calculate that this delta P is the power contributed by solar, it depends upon this H is the inertia, equivalent inertia of the synchronous generators. It's calculated in that way. F is your the frequency and rate of change of frequency. So it is going to decide this is the amount of power that is there because of the imbalance. How much, if this is the delta P is imbalance, this is how is the inertia of the system in photovoltaic system. And inertia in a power system comes from SG, means synchronous generator, and this is how we calculate it. How do you calculate the inertia? This W divided by this rating. So W is the kinetic energy stored. How much is the kinetic energy stored? There is no kinetic energy in photovoltaic. That is what we need to understand. But we can calculate the equivalent value of that kinetic energy which is stored there. And SSG is the MVA rating, or we can call it the generating rating capacity. Now, how do it emulate? That is what is important. Inertia emulation is realized by controlling the charging and discharging of DC link capacitors. If you see this, I don't know, this capacitor here, this is a DC link capacitor, and adjusting the photovoltaic generation when it is feasible or necessary. So it means it is the stored capacitor, its charging and discharging rate need to be controlled. At the same time, we also control the generation of your photovoltaic. That can also be done. This is how it is going to emulate the inertia. We simply take that if there is a load change, frequency goes down. If frequency goes down, it means the increased load, who is going to supply the energy? That is being supplied by your, the decrease in kinetic energy. Fine. So ultimately, it is supplying your active power to that. Basically, it's the supply of the active power, maybe by decreasing the kinetic energy. But it is essential to decrease the kinetic energy because it needs active power only. So if we are able to supply the active power by effectively controlling our solar panels, it is equivalent to that. It is equivalent to that. That is what is the virtual inertia. That the moment, because it is automatic, it is inherent in case of your rotating machines, that it is going to decrease the speed because increases the load. And that decrease in speed is basically going to supply the active power, additional active power. So the same active power can be supplied from the renewables also. It is being, tried. It is being studied, researched, that the moment the same kind of behavior should be there from the renewable for photovoltaic also. We should make use of photovoltaic panels, a photovoltaic system, to supply the active power in a similar way as is being supplied by a conventional generator or maybe by a wind generator. So that is what we call as virtual inertia. It means the inertia is not available as such, what we say, but yes, it can supply that. So that is what that we can control its charging and discharging rate using these capacitors, and adjusting the photovoltaic generation also. The two simultaneously actions that is being done. Now, to emulate the inertia of synchronous generator, the virtual inertia coefficient of a photovoltaic can be calculated like this. See, H is equal to, if you see the previous equation, same kinetic energy to by rating. So equivalent value we have taken up here as H means equivalent inertia from the photovoltaic. HPV means equivalent inertia from the photovoltaic. This one is the kinetic energy stored in that, and its rating of the plant, whatever you have, the photovoltaic plant. Okay. Then the frequency dynamics of photovoltaic system during the inertia emulation, means what are the frequency changes when it is responding to that uh, change in load. Yeah, it is acting as a inertia contributor. This is how we can have delta power change. Similar to that, delta B H by F that we have 2H by F. We generally have total H is the total inertia of all the system. So here also we have H photovoltaic now, equivalent value of the inertia that we expect from the photovoltaic. Okay, frequency and rate of change of frequency. This is how we model it. We are going to model it basically, that if there is equivalent change of power from the renewables, particularly photovoltaic, what is the inertia contribution of that? So this is how this modeling is done, and we are going to supply this delta P, the change in power, and that change in active power generation of photovoltaic for the inertia emulation. So what I am trying to tell you time and again is that it's a very simple concept, that we need to make photovoltaic panels, a photovoltaic system, to supply the active power the moment there is any change. If it is going to, if there is a load increase, it need to generate supply additional power, maybe by capacitor charging discharging, or by increasing the generation from the your photovoltaic. But how can you increase the generation from your photovoltaic? It is not dependent upon, you don't have that. So what is done there is that you keep some backup. If you have 10 kilowatt plant, so you use 9 kilowatt only, you keep 1 kilowatt spare, again a sort of reserve, that in case there is a load increase, you start generation, you connect it immediately. There are ways to connect. We have electronic technologies available nowadays. So we are making use, because it is the need of the hour. Because if the share is going to increase, it is going to, it has to be there. Otherwise, system cannot work. Now, there is some mechanism, so I will not go into depth because it needs some modeling and all these things. But yes, the power, the initial power that you have, and delta change, whatever you need, how much power you need, that a photovoltaic system need to be applied, updated generation setting. So it keeps on giving that continuous data, and accordingly it can set. What I told you, that if you want 1 kilowatt additional generation, so we already have kept that. We cannot start generation increase from photovoltaic all of a sudden. It's not a thermal or hydro units, but you can keep something in balance. Obviously it's a loss, no problem, but we need to keep it for the system security purpose, a stable system of operation. If there is a decrease in generation, then it is easier, because we can use it for storing purpose. So what is important here is, the important is that we need to have a very effective control. The algorithms that we need to have, they need to be intelligent enough, so that they decide, that they are able to take the decision depending upon the change in your system. And particularly, it can be again small signal or large signal disturbances that you need to model and accordingly study. So inertia emulation implemented, this is the way it is implemented. The delta change in power is through DC capacitor link and photovoltaic panel. So what I mean to say is that this is what you need to keep in mind, and if you are interested, so you can search it slightly, that the contribution for the photovoltaic is from the two sources. One is the capacitor, which is there used, okay, for storing purpose. It can, the charge and discharge. And second is the photovoltaic arrays generation itself. You increase or decrease it what I told you already. And this is how it can supply that additional amount of power that is needed to meet any load change in the system. This is one model. There's some latest papers. I can share it. So this is what, if you see the simple system, we have photovoltaic array. This is again boost converter, then your link capacitor, then DC to AC converter. It is connected to the grid. So what is being done? If you see this here, what I told you that it is the this capacitor and the photovoltaic. We need to develop this algorithm, this small, modeling that you need to do in Simulink, and you can control this delta P change. Which, if you want to, check your control the generation from the photovoltaic also. So this is how we can get it here at this point, and we add it at this point, and ultimately it is going to be supplied. And along with that, we can also use this DC link capacitor. This is how we can make use of photovoltaic panel to supply the additional amount of active power, which we call as the virtual inertia. Okay. So these are control strategies. So there are lots of paper available, but this is the basic concept which I wanted to tell you. Now, what about the wind? Wind is also having large share, and it is increasing. It is scattered also. That is why we call it distributed generation. And if large amount of share is there, it is going to decommit what we say is conventional generation. If total generation is of 100 megawatt and 30 megawatt is from the wind, which I told you earlier also. So if 30 megawatt all of a sudden goes off, it becomes a problem. To start them, it again becomes a problem. So we are using various DFIG, double effect induction generators, and many other types of generators, SCIGs and PSMSM. We can use anyone, but again, the change in frequency can be given by, this is how it is related, the power change, the inertia in case of your wind. The same problem in that case also. But yes, it does have a inertia. Wind unit, it has a inertia. Means it is rotating in nature. It can decrease its generation. So how does it respond? This is the basic. I will not go into depth. That this is the power, area, velocity, and all these things. This you must have already gone through. So we can generate this amount of power. Fine. And this also must be known to you. Badge limit, that we are not able to. Have you heard about this badge limit? But those you are not studied. But we expect, if you see this particular relationship on power equation, so if you see the velocity is having some value, so it doesn't mean that we are going to get that much amount of power. We get power up to 59.3% only. You can have this look on this equation where we are putting up these values, and we know that total amount of power which is there. If we have this velocity of 10 meter per second, we expect it to be 2.4 kilowatt, but it is not actually 2.4 kilowatt. It is only close to 1.4 kilowatt. Okay. So means complete velocity of that, it is not being utilized. It is never utilized basically because of the nature of the blades of the wind turbine. So this limit is that it is the maximum amount of power, that practical limit we can say, the bat limit. So when we are calculating, these things have to be kept in mind, that total amount, what is the rated capacity of your wind plant. This is the curve which I was telling you, because it is important that we have, this is the curve on which it operates. Those who have studied, they know it well, that we have generally, it starts from 3 meter per second to generally we have 15 meter per second where it can operate, when units can operate. And if the speed is less than that, obviously it is not operated. If it goes above this rated velocity up to this cutout, we keep it constant, the power remains constant, and beyond this speed of 30 meter per second, we again shut it down, because it becomes danger for your blades and all. But if you see this curve, this is the operating curve. Speed can vary from this to end. How do we control it? Because It is directly linked with the frequency. So how do we ensure it? So we have to slightly go into the, you know, the system, wind system, and this is how, we will talk about this pitch control later. I will come back to this. Just dip speed and CP, which is fixed in such a way that we maximize the power out of this. We have two turbines in wind: horizontal axis and vertical axis. Okay, both have their different, advantages and disadvantages. Particularly, if you see the vertical axis, horizontal axis wind turbines, they are generally used for the higher wind speeds. We prefer it for the higher wind speeds, and it is connected to a hub. Rotational speed will depend upon the fluid geometry. Now, what we have a gear mechanism, the generators, so it is able to control it. It controls it based on this gear mechanism and all. If speed is less or speed is higher, so it controls within that range. It is able to control it. So there are some, control available inside this which need to be studied. But this gearbox, this can control its speed to a certain extent between cut-in and rated speed. Vertical axis, though, it is used for the lower wind speed generally. However, mostly it is the high horizontal axis which is preferred. But for lower wind speed, this is also there. There's a number of new, type of designs which are coming up now. The material being used, there are lightweight materials. It also need to be seen because, uh, you know, over the year, it's there are some sort of fabric materials which are coming up, lightweight fabric materials which are coming up, which is able to operate at a very low speed also. So, but these two design, vertical and horizontal axis, they particularly preferred for higher and lower speed, and they're on their own advantage and disadvantages. Now, how do we connect it? That is what is important. If we talk about isolated system, particular generator, if you see a high induction generator operating at a particular, speed, how can we make it to work as a generator? How do we, when does it work as a generator? In case it operates above synchronous speed, it should be the frequency we can calculate, and if we need to make it rotate above synchronous speed, so there are different mechanisms being used in isolated system. For example, if we have a 4-pole induction machine, and even if it operates at 1200, 1300, 1400 rpm, then also it can work as a generator, because the frequency is less, so it can work as a generator. But in grid connected, frequency is 50 hertz, so it needs to be operated at that particular speed only. So what you need to understand here is that when we connect it directly to the grid, then the frequency and the voltage parts is taken care by the grid only. It is going to inject the amount of current in that. It is not going to control the frequency part in that. Frequency is being controlled by the grid itself. So different topologies are being used for that purpose. Sometimes it is being controlled by the gear mechanism if it is an isolated system separately, but if it is directly connected to the grid, like we have different inverters being used, current mode inverters, we have voltage mode inverters. In current mode inverters, how does it operate? It is not going to regulate your voltage and frequency, because ultimately it is inverter being used that is to connect to a system. So they do not control your voltage and frequency there. It's just like the injection of the current. It is acting just like a conductor injected to that. If we say it's a voltage source inverter, there they regulate the voltage, right? So, like if we see this directly connected, simplest one, it requires such a, like we need to see that it doesn't work as a motor, okay, and it draws reactive power, okay, and there is no reactive power control. This is that different topology is being used. This is doubly fed induction generator. We have injection from rotor side. The advantage with this is that in case there is lesser amount of speed, so it can get it can feed it back, maintain that speed in such a way that it works as a generator, that it is being fed from the both sides, stator as well as from the rotor side. And if you see this portion here, so rotor is connected to this AC to DC and DC to AC converter. Again we have a gear mechanism. The advantage with this, I told you that because of this additional amount of, because how is torque is produced, obviously is the amount of flux that is available there. So how do you control it? We're going to control it through inverters. So you're going to feed it to the rotor. We inject, if you see the rotor speed control method, you must have heard about the uh, EMF injection in the rotor. So what do we do there? We're going to inject certain amount of EMF that can be in phase, it can be out of phase. Its magnitude can be decided, and accordingly speed can be controlled. But how do we inject that? Again through inverters. So here the inverters have to play that kind of role, that it needs to balance that amount of uh, power, and accordingly which EMF which is being injected, whether it is in phase with your rotor EMF or it is out of phase of that rotor EMF, and accordingly it balances that. So that type of methodology can be adopted here, and it has the advantage with that. Then this is another topology. So particularly this DFIG, PSMSM and CIG, they are being used nowadays. Means one is directly connected to the grid, second can be isolated. Okay, and there are different ways through which it is being converted. What is important is that whether it is in current mode or in voltage mode, which is controlling the voltage and frequency, that is what you need to study and understand. And accordingly, these are some models. There are models available nowadays for this simulation purpose. Again, this is again we are directly connecting it to the grid. It
Comparison between the last and this one.
which one?
Yeah, this one and next slide.
Next one.
Yeah.
See, if you see this here, this is doubly fed. You can see one supply is rotor. Uh, Rotor is being fed, okay, from the main grid, and stator is also there. It is connected to that. And if you see here, next one, there is no connection to the rotor. Okay, directly connected to the grid only. So it means rotor EMF. How rotor EMF is rotor is rotating. Okay, rotor is rotating means the EMF induced in the rotor will depend upon that, because frequency in rotor will depend upon SF. So S is basically dependent upon the rotor speed. And in case that speed is directly regulated by the wind speed only, so whatever is there, it is going to be connected to the grid here in this case. But here we can regulate that. If speed is not less, what you can do? Whatever supply we have, we can inject some amount of current in that. We're going to inject that and we can control that speed. That is what is the advantage with doubly fed induction generator. Doubly fed का मतलब ये है. Got it? So we have a slightly better control in this case as compared to these topologies. So generally, if you see the present scenario, it is these are the topologies which are being used nowadays, because we need to have effective control. Yes, in case I told you in isolated system, maybe in island or somewhere where it is not connected to the grid, then there is no problem. Even if it goes down to frequency, you can maintain that and still it works as a generator. But for when it is connected to the grid, then we need to ensure that it also need to have proper control, and motoring operation should not take place. Okay, otherwise it start working as a load. This is how it is connected. If you see this, the perfect diagram, the wind speed you can have. We have a control. We can control these rotor side converter, grid side converter. I need to see whether it needs to be supplied to the grid or it has to take from the grid, and ultimately it is going to supply to the rotor through slip rings and control its speed. Okay, so it is injecting that. So the injection is possible, and as a result of that, it is very effective. Okay. Now this is how they go. DFIG stator is normally connected to the grid, and rotor is supplied via frequency converter. That is what I already told you. And this is how is the relationship that depending on the direction of the supply frequency, this machine can operate over and under synchronous speed. Okay, this small relationship that you can go through the papers. There are some papers available, but what is the important point is that D5 and PSMSM, these are being used nowadays mostly when we say the grid. There are hybrid system, microgrid systems which are coming up. These are the energies. The change in energy depending upon that, it can be supplied by this. Okay, this DFIG wind speed, there's some relationship that how much is the kinetic energy released, the change in kinetic energy depending upon the this inertia of these two. Now variable speed. What is important in this case is it is a variable speed. DFIG is basically a variable speed. The focus is on DFIG particularly, that there are fixed speeds and variable speed. Fixed speed that you cannot do not have any control. Here we have the control. And here in fixed speed turbines, they are prevented to supply their maximum available power in normal situations. They will supply whatever they have. With but with variable speed turbines, extracting the kinetic energy in mechanical system of the wind turbine is easier with modern power electronic devices. We can operate it at in a particular point where it extract the maximum power. That is what is the advantage with the variable speed. Both of them can work, but if you want to make it, because their speed is varying continuously, and if I want to make it operate at maximum power, we want that maximum power should be extracted. So it is possible, quite possible, with the help of this variable wind speed. Okay, whereas in fixed speed it may not be possible. So it is going to supply, but may not be maximum power all the time. Okay, that is the advantage with this variable wind speed. Now, how do we use? Again, what do we do? We have inertial control because inertia was the main topic. Power reserve, and there are some other methods also. Now, inertial control in this case, it has two ways, two different methods to supply it. Okay. Again, we need to go slightly in mathematics for this. That first it supplies this inertial, uses this inertial response, and other uses the Droop characteristics. Droop characteristics you must have seen studied in case of generators when we see the load frequency control. Okay, that the power and speed relationship, that how much it is supplying. If we the first control, it makes the wind turbine to respond to frequency disturbances. This control, initial control, what it does, it responds to frequency disturbance, and the amount of power supplied by the wind turbine is proportional to the derivative of the frequency, because frequency is changing continuously. If it is a step change, it can adjust its power to that, but load change is continuous in nature. So it is the rate of change of frequency also that also need to be considered. Got it? Means load change is not changing at this one minute and after 5 minutes changing. No, it's continuous. So we need to see that if it is significant, so it also takes into account the derivative of the frequency. The frequency की से change हो रही है, that also need to be considered while designing a control mechanism. In case of second control strategy, which is based on Droop, the amount of power supplied by the wind turbine is proportional to the difference between the measured and nominal frequency. Aapka, what is the nominal frequency and what is the actual frequency of the system which is operating? If there is a difference, it will adjust it accordingly. Okay, and do that. But again, it's not taking a derivative. It is momentum, responding at one point of time and then waiting for another one. This is how reference we set. These are the coefficients, rate of change of frequency and the frequency. कितना आपका frequency है. This is how it responds. So wind unit inertial control loop, it sends an additional active power to variable speed wind turbine, and active power reference P reference is quickly and it changes to active power. So what I mean to say is that in case of this inertial response, an additional reference power is set based on this relationship, which is considering the rate of change of frequency. Again, I'm emphasizing on this that there can be load change, frequency changes, it stabilizes. That is one condition. The another condition is that there is change, then further change, and frequency keeps on changing. It is not going to be stabilized immediately, and it is happening. If you see your Northern Region Load Dispatch Center website and you monitor the frequency, so frequency is continuously changing. It cannot be maintained 50 all the time because load and all these things are variable in nature. So that is why it is important that in certain control mechanism we also consider the rate of change of frequency also while designing the reference power. And this is how this inertial control schematic works. Okay? So we have ultimately what it is doing, it is again supplying it to the rotor side converters. Some signals are being supplied so that through that only it is going to supply the power. When from the wind, what we are doing, we are again supplying to the converters only. So we do have this power angle curve. Okay? Reference frequency, we have system frequency, and we use some some filters and these coefficients which I told you already, and we set reference power which is based on rate of change of frequency. You can use it without this also, but if you consider it, so it is going to be more precise and more effective control because frequency is changing continuously. And then we generate it, compare it with this, what's the actual power being generated, what's the reference power, and it compare it and accordingly give signal to the rotor side converters. Yes, now you need to fire, increase or decrease. This is, we are talking about a DFIGs. You set a reference power, you have the actual power, and the reference power is being set in such a way that it is considering the rate of change of frequency also. And if there is a difference, so the difference is conveyed to the rotor side controller, and it will fire that converter in such a way that it is going to inject the current to the rotor by a certain amount so that it starts supplying that amount of power, so that which is equal to the reference power. Now limitation of this control, there is a limitation of these controls also, that it masks the load change and delays the response of conventional generators. This is what we will, I will show you some results also which we have taken up. Now what happens if we compare a wind generator and a conventional generator? I told you that the response, the reserve, the frequency control, primary frequency control, secondary frequency control. Primary frequency control, we say it's 0 to 10 seconds. Secondary, maybe 30 and up to a minute. So what happens? These wind units are very fast to respond as compared to conventional generators. This is what is the advantage with this also. That the moment there is a load change, wind unit will act fast. Immediately they will decrease their speed, but they cannot supply power for long. That is what is the limitation with that. But if they take up that load change, the conventional generators, they observe or they feel that there is no load change at all. Why? Because it is being taken up by the wind. But wind is taking momentarily only. It is not going to supply it for long. That is what you need to understand. It no doubt responds immediately. It is faster because the conventional units need to start generation, maybe increase heat input and all these things. So it takes it, but after some time it surrenders. And if conventional generator has a feeling and it gets a signal that there is no load change, then it again becomes a problem for that. So it need to be coordinated. This is what is a challenge. It's a challenge area research still in virtual inertia concept. This is the area that is still being worked out, and their power electronics people have a major role to play in that. That the moment wind power, I will show you the results. It increases the generation by decreasing the speed, and simultaneously after some time that power generation will decrease. Wind is not going to supply it for long. The moment that decrease in generation starts taking place in wind, a signal should go to conventional generator also. Yes, you need to start generation now, because ultimately it is the responsibility of that generator only to take up that one. Okay, so that communication has to be there between the wind unit, which is decreasing because of its inherent nature, and the conventional thermal unit, which need to take up the generation finally. So that communication has to be there. So we are talking about only, I have not taken the photovoltaic right now. That is again going to be another point. So we have photovoltaic at one point, wind another second, and then we have conventional units like your thermal and hydro. So the limitation is that if it is not properly controlled, or we can say there is no proper communication, so it masks the load changes. It is not going to make your conventional unit feel that there is any load change, but ultimately after some time it will come to know automatically, because wind cannot supply it for long. So second is that the wind persistence being limited, power reserve cannot be granted for the short term. This is what I already written. So it is not going to supply it for long, and does not investigate the limitations of variable speed wind turbines like current and voltage rating of the converter. So this is what I told you, that it's a challenge for power electronics people, that they need to. It's a huge area of research that is coming up in power electronics area, that how to design these converters and inverters with the existing system that we are coming up. The second is the power reserve control. We can keep some power reserves. What I told you in that virtual inertia also, that increase generation from solar, it cannot be increased all of a sudden. Yes, we can, but we can keep some reserve. Here also we can keep some reserve. Can you keep some reserve from the wind also? Photovoltaic is fine. Whatever evening generation you store it, you keep it, because that is already there. You just need to connect it. But what about in wind? How can you control it? Pitch angle. Pitch angle control is, most of you you must have heard. And if you're not heard, so it's very simple to understand, that you just need to change the wing direction, and you expose it higher or lesser depending upon the direction change. But it again, it has some limitation. It cannot go beyond a limit. So again, within that range of cut in and rated speed, it can operate. But yes, you can still control it. Then we operate wind turbine at increased speed. This is also again a possibility, because how can you operate at increased speed? You already have a rotor, DFIG is there, operate at higher speed. If you're operating some of the wind turbine higher speed, what does that mean? If there's a load change, what it will do? That increased speed which you have fixed for that, it is going to release that kinetic energy to supply the load. But again, how much is the increased speed? That is also you need to see, because wind turbine can always operate at a higher speed. Then only it works as a generator. So you can keep it slightly higher, but again, there need to be, it's not you can keep it very high. But yes, you can keep it higher, and as and when needed, it is going to supply it. This is how you can control. So this I already have discussed, pitch control. This is all is the curve. Optimum for optimum power generation. This is what I can control it. How do I control it? By DFIG. I all told you. But what we do is, we do not generate the power, full power. We keep some power reserve. You need to keep it, because inertia. When I say inertia response in renewable, because we know it is highly intermittent, so we cannot always. If we are operating at the optimum power? What does that mean? It means that generation. It is a message. This is the generation available. Accordingly, load is being supplied. But if you supply 95% only, and you have the option to increase it to 100%, so 5% is available to you. As and when there is need, you can increase it. So that is what is the strategy being adopted. That let's not use it at the optimum value, keep it reserved. So there is, and this smart grid has made it possible now that we can do it. We can control individual, we can control different photovoltaic or maybe these units. The power change, that active power curve, what is, what should be the speed, and accordingly how much power is being delivered. That curve, you can see that amount of power which is being supplied in these curves, and we can find out that what is the change in power that is needed depending upon the speed. How, what is the rated power, actual power, what is the change extreme power that we can have, and where we can operate it. The purpose is to keep some power in reserve and operate it at a slightly maybe on higher speed, or on this curve slightly generating lesser power than the optimum power. Then communication, I told you, it is very important that a message between different units should be given so that they do not take it that there is no change at all. That is one area that is coming up now. Storage is becoming a very important area of research. Particularly, we are having now batteries, lithium ion batteries are coming up. They already are there, but and in addition to that, we have super capacitors available, flywheels are there, fuel cell. So many devices are coming up, and they are fast to respond. And particularly in, if we see the isolated area, microgrid, they are sufficient. Storage, they may contribute a significant part. So they can supply the reserve or change in power. Whereas if you see the largest grid, so they may not be significant. Now we have now different combinations, like we have batteries. Batteries can be started instantaneously. You just need a firing circuit, and on a fraction of a second, if, through controller, you can start generation. You can supply active power through inverters. Can we supply reactive power through inverters? Photovoltaic, can it provide reactive power? That is what you need to think. That I will discuss it later. So focus on the active power first. So what I mean to say is that now you have batteries, you have wind, you have hydro, you have thermal. Different characteristics. They all have different characteristics. If you see the batteries through inverters, you can fire it instantaneously in fraction of a second. So it is the first, you can say the component to respond to any load change. Then comes the wind, slightly slower than the batteries. They need to be, again regulated. And after wind, it is hydro, which can act, and hydro then thermal. So all these units, they all are responding to the load change. Battery can supply for quite long amount of time. Wind is for smaller amount of time only. Wind cannot supply for long, but it is faster as compared to thermal. So the area which is there, that you need to coordinate the operation of all these. Batteries means batteries plus photovoltaic cell. आप उसको लेके चलो. Then you have your wind unit, and then you have your conventional units. How do you make use of them for supplying active power? And they should be, because they have different time of operation, and they should be coordinated. They need to be, there should be communication, proper communication, that now it is going to supply this much only, next should take over. So that strategy need to be devised for the inertial response. This is what we already have discussed, that in DFIG, what we have. Now, there is slight difference. That reference power which we have is, we take into account the reduction of frequency, as well as this one that is called as your speed function is also taken into account. So a model has been done. This is what I have done in one of my papers. So what we do is that we measure the frequency through this measurement. We have a reference with this power here. Then I have used these controllers. this is inertia of your wind, and this these are the power that I can control using your PI controllers here, and I supply it, and ultimately this is the power generated from NC means non-conventional sources. So this is a one DFIG linearized model, DFIG linearized model, which is taking into account the frequency change continuously, rate of change of frequency also, and we are in a position to get the change in the power from the DFIG based on the frequency as well as the frequency change. Okay. So this reference power can be obtained, delta PF can be obtained from here. This is simple system. If some of you who are studying power system, we have a single area, a single generating system. What do we have? What do you call this? Governor. This is governor. Okay. First order function. Then we have this turbine, and this is generator, load plus generator. Okay. And here we have the load change. Del PD is load change. This is a model, load frequency control model. Normally those who have studied power system, they understand it. And this is your non-conventional sources. This is how we are injecting it. We will connect it here. The power of DFIG, the model that I have made. So what I did is, in total amount of power, if you see, delta PG, power generated from the conventional unit, power generated from the non-conventional unit, because both of them are supporting the inertia. Delta PI, P12 is your Thailand power, which is from the other area, and del PD is your load change, and this is your del PM. How much is the power change? This is how you can calculate, because this is all the powers are being calculated. The generators are contributing to increase the speed, whereas load is opposite. So there is a balance between the controlling and driving torques between the two. These are some equations. This is how we uh, calculate the inertia contribution based on the power generated. Normal string equation you must have studied. So from there we can find it out, and we can find the wind generation share. If there is a 100 megawatt, if 30 megawatt is 20 megawatt is of wind, so 20 by 100 is 1/5. So that is what we can find, 20% wind share. So we can calculate this. H can be decided in such a way that I am increasing the generation. So this is one model that I have taken up. There are number of addition that we have done now. We have considered restructured more power market nowadays. If you study this, this is one area system, and this is another area. The two area system that we have in load frequency control. Normally, these simple regulators. What is important is just DFIGs. These two DFIGs. So I have connected these DFIGs in two areas separately, just to see that how do they respond. Okay. In conventional unit, there is a single generator only, but I also have one DFIG. Now we have worked. The research is presently the students are working where they have included the photovoltaic batteries. Along with that, not only for two area system, multi-area system also. Along with that, we have considered the restructured power system where demand side participants are also taking place. They are also contributing towards this. And this is a simple model that we have. These are your generators, and we optimize these parameters. This is what, like I told you, that we are these. They are PI controller which we are using, so we can optimize like this. I integral square error technique which we are used. There are some other techniques available nowadays. We can use PSO and GA just to find the gain of your P and I. I think in latest version you can directly get it optimized. Okay. So what the purpose is that we devise a function where we want to minimize this frequency of area 1, frequency deviation of area 2, and tail end power, which is there. This frequency deviation here, because we don't want any frequency deviation. I need to minimize this, and based on that I can find. So what I am doing is I am changing these wind units, you know, uh, proportional values, gain values. and I plot them, keeping one value constant, varying another, then keeping second value constant, varying the second first one. This is how you get these values, and you can find the optimum value of the these gains. This is how the response comes. That is what we need to understand. If you see these two frequency curves, this is blue color, it shows when there is no DFIG. In second case, when there is DFIG, you can see the peak, it goes down and it settles faster. So what I mean to say is that the disturbance is in area 1 here. That in case there is a wind will respond fast. Wind will respond fast means the frequency deviation will die out faster as compared to the system where there is no wind unit. Now, if you have battery, it may be slightly better than this. Okay. Now, this is a tie line. How the power is, varying between these two. This tie line power that we have calculated. This is the area control error. Again, you can find the improvement with that wind unit because it is responding to the load change, and it is settling time, peak time, it is smaller. This is the contribution of the two units. If you see conventional units, the system that I showed you, what is there? There are two units, conventional units, area 1, area 2, and then we have two DFIGs, both the areas. Now, if you see this area 1, this curve, this blue one is PG1, means generation of unit 1 without DFIG. And this is the generation of the second unit with DFIG. And when we connected DFIG, you can see this is 0.03 here. It is not approaching 0.02 only. So it means the generation of the conventional generators has decreased in initial intervals when there was a wind unit. Why? Because wind unit is ready to respond. It has inertia. So I told you again how to, it will respond, but it is not going to supply it for long. Now, how can you see it? If you see this, the generation of this unit is no doubt lesser. Because this is the commercial unit. Generation is lesser, but if you see, this is going to increase after some time. Here you can see it is 0.02. Where it is set as 0.02. Why it is why it is increasing? It is going to increase because ultimately this unit has to take it up. Wind unit cannot supply this for long. But yes, it can support it in initial intervals, and it complements the conventional units because they are slow to respond. That's how it becomes very important that we combine these generation, make a hybrid system, and make use of them effectively with effective control that they respond to each other, and they overcome each other limitations also. There's some regulations we can control. These are values, regulator which we have, group control which we say, and we can see the speed change, the decrease in rotor speed of wind unit 1, decrease in rotor speed of wind unit 2. Speed are decreasing. Obviously, there's a load change, it decreases. Now, if you use the regulate, the group control, so it is different in different for different values. Now we considered load per day at different intervals. Initially we picked up, and after 20 seconds we again introduced a change. The load change is step change only. It is not continuous change. That is what I am telling. It is important that rate of change of frequency also need to be considered. Continuous load change. We are changing at different intervals only. It need to respond to those changes. And here, in both the cases, it is going to respond. So it means when there is a DFIG, it not only supplies that active power, reduces the peak, as well as reduces the settling time also. That is what is important. we should make use of the wind unit, and we have the control mechanism, and polytronics is developing, and effective controllers can be designed, and we can make use of these batteries, what I told you, batteries plus photovoltaic, very fast to respond. Then the wind units, slightly faster than conventional, and then ultimately conventional unit need to take it up. Okay. And what is important in this case is that if we include the restructured power system where we have the load, the site participation also, then again it becomes a very complex problem, but very interesting also to solve. The share, it was also important to tell. I told you I give you a relationship out of total power. How do you decide it? You can find the inertia contribution from the wind. H value you can fix up in that particular model. And 5% wind penetration, 10%, 20%, and you can increase it up to a certain extent. And how the frequency is going to, obviously you can see that more and more of this uh, contribution, deviation goes down. Why it goes down? Because they're going to contribute. They're going to respond in the initial intervals. That is what we can see here. Right? Same for the area number 2. For all these, again, the contribution of the different generators. I told you in initial generation, which was there higher, it is not no longer there. There is no peak. But ultimately, if you see, it is increasing continuously. Why it is increasing? Because these generators need to take it up. Wind cannot supply for long. That is what we need to understand here. These are some of the values that we have obtained. Just for your information, we can share it for different values, overshoot, undershoots, and what are the values, optimum values that we have, you can say, tuned using integral square error technique. So I would like to conclude here that we can have a discussion, because I think it's almost 5 minutes left. That it is very important that we make use of our renewable energy sources to contribute towards the inertia. Because photovoltaic as such doesn't have any inertia, and they need to supply it, and we can make use of this. Okay, we already discussed about that. How can we make photovoltaic unit to respond to inertia? Similarly, wind also, but they have different characteristics. They need to be coordinated. So for coordination, we need communication and effective or polytronic converters for that purpose. And if we do that, I think even if we have 20, 30, and 40% of penetration of renewable energy sources, we will be in a position to sustain our power system under adverse conditions or high load changes also. So that is what I wanted to tell in this lecture. And if you have any queries, you are most welcome to ask me. And there are some papers on virtual inertia. Those who are interested in this latest paper, because there is very little work in this virtual inertia, but people are working. There is huge research going on in virtual inertia area.
Nodal centers, if you have any doubts, you can just clear it. We have 5 minutes. After that, we'll break for tea and again reassemble for the next session.
Some papers that where I have used it.
Clear, participants. Nodal centers. I think now we'll break for tea and we will just reassemble for the next session at 11:35. Okay, we will reassemble so at 11:35. Now we'll break for tea.
अरे इट वुड हैव बीन बेटर अगर चलो ऐसे हमने ध्यान नहीं दिया कि अगर ये अपने लैपटॉप पे ना डाउनलोड कर लेते एंड साइमल्टेनियस एक का था तो दैट मेक्स सेंस. हाँ 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 just for information ma'am if you can see these are some of the equations of uh, fact devices. So what we do is कि what is the power being injected by a particular fact device that we use in load flow equations. So at what bus it is being injected that we can fix up. Okay, you can vary it, see its response. So normal power flow equation, if you see these power flow equations, actually इसमें थोड़ा power system वालों का थोड़ा this is हाँ any yes this is fact device this one दिया हुआ है and this is TCPAR this one then I can show you UPFC. This is UPFC. These are UPFC equations. Well, so what we do is we simply add, like in normal power flow, what we do, we simply uh, write equations, the power injected from generators. Okay, and these are some of the equations like this: PG I minus PDI is equal to P injected PI. Okay. So what is PG? PG is the thermal generators wherever it is in different buses. This PG will also include your UPFC. But so what do you write? PG will be equal to P thermal plus P facts जो भी आपका है. तो जिस बस पे होगा उस पे वो ऑटोमेटिक पावर दे देगा. बट वी नीड टू राइट मैथमेटिकल इक्वेशंस फॉर दैट. तो इक्वेशंस ही लिखनी है इसमें और कुछ नहीं है. एंड डाटा नीड टू बी सप्लाइड. इनपुट डाटा से आपका व्हाट्स द रेटिंग इफ यू आर टेकिंग रेटिंग ऑफ योर फैक्ट डिवाइस. तो दोज इक्वेशन, हाँ वो आपको वो तो दैट आई विल शो यू कैसे करनी है वो. पर आप मैं छोटा प्रोग्राम लूंगा क्योंकि बहुत बड़ा है, इसमें कंफ्यूज हो जाते हैं बच्चे. इनफैक्ट अपने जो पीएचडी के 3-4 लोग हैं मेरे पास, तो मैंने उनको सबको ये आई लर्न इन द कह लो थर्ड फोर्थ ईयर ऑफ माय पीएचडी. सर तो कहते थे यहाँ कर लो ये ले लो ये ले लो. मतलब इट वाज वेरी डिफिकल्ट टू लिंक इट. डाटा कैसे लेना है क्या करना है चीजें थी. For example, I want to insert DG at a bus number 14, for example. वो कैसे करना है समझ था. चलो टिम्पल एक टाइम के साथ वेरी करना है, विंड लगाना है, आप 24 आवर्स वेरी भी करना है, लोड वेरी कर रहा है, वो चीजें सो मेनी थिंग्स. वंस यू स्टार्ट वर्किंग कॉम्प्लेक्सिटी इतनी ज्यादा होती है कि एंड फॉर ए स्मॉल प्रॉब्लम इट टेक्स मंथ्स. जब आप उसको अब मैं देखता हूँ कि इतना टाइम वेस्ट किया था इस चीज के लिए. दैट इज व्हाई आई टेल माय स्टूडेंट्स, इवन आई गिव देम डेमोस्ट्रेशन. मैं उनको बताता हूँ कि आते हैं बार आते हैं हमारी फैकल्टी दे अपोज कि आप तो प्रोग्रामिंग कर सकते हो, बट इट्स बेटर कि भी जो चीज हमें पता है, आई डोंट वांट माय स्टूडेंट टू वेस्ट टाइम फॉर दैट अननेसेसरली. और वो छोटी चीज होती है, दे डू इट इमीडिएटली. वो उनको इस लेवल तक पहुंचा देता हूँ. दिस इज व्हाट इज अ लेवल नाउ. नाउ व्हाट यू नीड टू अंडरस्टैंड इज दैट यू स्टडी अबाउट द योर ऑब्जेक्टिव्स. वंस ऑब्जेक्टिव इज क्लियर यू कैन मॉडल इट. तो यू फाइंड डिफरेंट प्रॉब्लम्स. यू शुड नॉट बी वरीड अबाउट कि मैं कौन सी टेक्निक लगाऊंगा क्या है. टेक्निक वाला पार्ट खत्म है इसमें. आप बाकी पीएसओ जीए वो लगा दो, वो जो करना है आपने. ग्रे वॉल्फ बहुत सारी चीजें आ चुकी हैं दैट यू कैन यूज फॉर वेरिफिकेशन. बट दिस इटसेल्फ इज वेरी एंड पर्टिकुलरली स्टोकेस्टिक्स में बहुत सारे फीचर्स हैं मैम. ये तो मतलब अनएक्सप्लोर्ड है, अभी तक इतना कर भी नहीं पाता है. अदरवाइज इसमें तो इतने अच्छे मतलब फीचर्स हैं कि भी यू कैन टेक अप एनी काइंड ऑफ प्रॉब्लम. हाँ वी कैन स्टार्ट नाउ. हाँ यार.
Very good morning. So we are going into the next session. It is power system optimization using modeling in GAMS. Okay, so I hand over the session to Dr. YP Verma.
Thank you, ma'am. Optimized study in power system has uh, become very significant, and we always come across the problems where we need to maximize certain function or minimize certain functions, and that is what we call as the optimization. There are a number of techniques available. We talk about the deterministic techniques, and nowadays we also have probabilistic techniques like genetic algorithm, PSOs, and gray wolf, anti-clone. There's so many optimization techniques available. But conventional techniques are generally considered to be the reliable one and the best one. Why we switch over to the probabilistic technique is that there are certain functions which sometimes become difficult for us to solve in traditional or these optimization techniques. So that is why we move towards that. But GAMS provides that platform which takes into account all the complex functions also. Like if you have exponential, hyperbolic, and all these things can be taken care in this. And what is more important in this case is that it provides you the solvers. You need not to worry about the optimization uh, techniques. For example, whether you want to go for the particle solver optimization, we just need to select a solver. What kind of solver we need for the problem, that we should have an understanding, and we select it and it will work. And that solver, how it works, there is again literature available. You can study that. Like we have branch and bound methods. We can also have lambda iteration methods. So many methods are being used by this software for optimization purpose. Now I'll pick up the power system problem first, the general problem, and then I will give a demonstration that how to write a program in the GAMS. The best part in this is that it can also be interfaced with the MATLAB. We can have data in the MATLAB, any standard system that we have, IEEE standard systems, and those systems data can be brought into this GAMS environment, and it can run that and then data can be given back to the MATLAB for plotting and all this purpose. So that is the benefit of these games, and it is being used since long, uh, and I feel that those who are pursuing and wish to pursue their PhD in this area, they can have it, and it is available. Student version is available online freely. So these games, it's not GAMES. Please note it down. So when you search, it is GAMS, General Algebraic Modeling System, and obviously high level modeling system. So what it has input file, then we compile it. We use this optimization solver. What I told you, that we need to stack the solver. That solver will solve it, because it's just like a function that will solve it and then give it back to this environment, and then you generate a output file. Fine. So what is important in this, just what are the how to uh, give the input files, how to select these solvers, and how do we write the output. Input files, any file name abc.gms. This is this gms, and output file will be any file name .lst. So you can identify by this only. So whenever, if you can select a folder, in that folder the file name gms.gms means your input file, and this will be your ist file, lst file will be your output files. The extension will be there, gms and lsts. So I will show you that, it will be clear to you also. They have different color itself, so that is easy to identify also. Now in games we divide into different sections. Like first we specify the indices on data. That means the sets and parameters. What are the sets and parameters? Sets are, for example, if we talk about a normal uh, optimization problem of power system, which we call economic load dispatch, which I will solve. I will show you. So in economic load dispatch, what do we have? We have generators, 5 generators, 6 generators, 10 generators, set of generators. So we define, let us suppose I as set. Now there is the time. It is working for 24 hours, 48 hours. So time can also be, time is also set for different intervals. So we need to define those sets. The parameters. Now parameters are the given values, certain values which we need to have. On the basis of that, it is going to calculate, they solve the problem. So they also need to be specified. Then listing the names and types of variables. We also need to define the variables. What are variables? And we write the equations. So equations, first we define them, and then we write the equations. And when we define, what are the equations? Equation can be like your any constraint that can in the form of equation, and it can be objective function can also be your equation. So that we need to write in GAMS. Then we can also have like initial values, boundary conditions. So those values also need to be specified. For example, if we talk about the power system, the voltage limits, we specify that it should be between 0.95 to 1.05. So these bounds need to be specified. Okay, so that it becomes easier for this to understand that it need to solve it. We need to explore anything, but within those boundary limits. And then we need to call the optimization solver. Those solvers need to be called, and we can call it. And in case you choose a wrong solver, it will let you know that this is the option available. You select this one. So depending upon the need of the optimization problem. The format of input file is flexible. Flexible in the sense that it is doesn't follow a pattern like from up to downwards. If you write equations, first equation, then third equation, then second equation, something of that sort, it is not going to cause any problem. Just like in MATLAB, it works sequentially, right? If you write something, first it will be executed, then it goes to next and next. It is not a case here. You can write anything. and it will automatically pick it up. That is the best part in this. You can add any time in between. If certain things you want to introduce at a later stages without making any major changes, it can easily accommodate it. That is why it is very flexible. It is not rigid. Then there are certain keywords that I will let you know, and it is very easy for this to model any complex system. I told you whether exponential, all these terms they are available here. Let's take an example. For example, if we see this function, we need to minimize this z, where we have three variables x1, x2, x3, x square, x1 square, x2 square, x3 square, subject to the condition, these conditions. 1 minus x3 by x2 should be greater than 0. Second, we can rewrite it in this way. X1 minus x2 square plus this is another condition. These are the boundary limits. X1 should vary between 0 to 5. X2 is varying between 0 to 3, and this x3 again between 0 to 3. You can start with initial guess normally. So any value you can pick up. Okay, but it should be within those limits. Now here it is important that if certain functions are given, because when you read a paper you can find equation written in this form, so we can rewrite it. Why it is important to rewrite? That is what is written in this blue color, that we can write in this way: x2 minus x3 is greater than 0. Why? There can be certain conditions, because once it is varying, it will come across as 0, and sometimes it becomes difficult for this, or it will not be able to solve it. So it's right, if you write this, that division by 0 condition goes off. Okay, and similarly uh, there are other small changes that you need to make, that I will let you know, that can make it easier, and there should not be any problem and while writing it, while solving the problem. Otherwise it can sometimes lead to certain errors, like we also put up certain tolerance limit. So those tolerance limits also need to be there, because computer cannot have that exact zero, balancing between maybe two parameters. So that mm, we can stopping criteria should be in such a way that either we fix the iterations, or it should meet that, that you can say the conditions, or we can call that epsilon that we have picked up, the tolerance limit. This is how it looks like. First is the dollar control commands. I will let you know what it does. Then we write comments. Like if you see the MATLAB, what we do, we use this percentile sign. It makes a comment. Then it is a star. So that will become a comment. So I will show you, then it will be clear to you also. Then the program main code looks like this. Okay, like variable. These are the keywords which we discussed. Variables, equations. Then we write the equations. Some syntax are there that can be discussed. And the solve, last one. Okay, if you see this solve, we'll pick up this. In first dollar command, here this dollar title, this option sets the title in the page header. Because if you do not do it, hardly matters. But these are some standard formats. If you do it, fine. If you do not do it, hardly. Okay. So similarly, we can have this on sim reference. Then we have this the collection. This option controls the collection of the cross references for sets and parameters. Cross references for all the symbols. Listing files is also there. It tells you each and every step of the solution also. That is the advantage. It also has some debugging. It tells you that at what step there is it is going, solution is going infeasible. You can make that changes and make it feasible also. So that is the advantage, that if you solve any problem, you need any algorithm or any technique, you do not go see the steps at what particular point of time it is going infeasible. It gives you that advantage. Fine. So there is this GAMS tutorial available. You can find it out. There's some examples also that you can. I think it's available. So that you can easily assess. Now input file. First, I told you this is input file, like variables x1, x2, x3, because we have these three x3 here. This is the example that we have picked up. Z is your objective function. So these are the variables. X1 is also varying, x2 is also varying, x3 is also varying, and Z is also varying. So the key word here is that is use of variable. Variable is important to we need to write variables, and then we write the different variables. We specify variables. I will show you the program, then it will be clear to you. Then Z, it is also variable. That is your function. So its objective function, it must also be included in the variable, because depending upon the value of x, Z is also going to vary. So it is also a variable. It also need to be included while defining it. Then there are certain variables or which are to be kept positive. There are certain variables which are binary in nature. So we need to specify with that whether it's your positive variable or binary variable. When the moment we write it, it will pick up those values only. Like if it is binary, so it will pick up 0 and 1. Okay, so that is what is the advantage with this. And objective function value should not be included here, as in it might take positive, negative. So it means objective you cannot fix positive or negative. Like if you have to maximize something or minimize something, it can have any value. For example, depending upon the input value that you are given, it can give you any value of objective function. So if you keep it positive only, so it may result into infeasible solution sometime. For example, if I want a profit maximization problem, so I want profit to be maximum. I can write it maximum, positive function, but profit can be negative also. I mean that means you can be in loss. So while solving, it can be in loss. Negative value means you are in loss. Okay. So if you fix it, so it may show that it is not feasible. So it can result in. So that is why objective function need not to kept in the positive variable. Semicolon is needed after every equation that we will specify so that it ends the list. Well, it is good for the ending purpose, just like your syntax we use. Now, here equations is another keyword. We first of all define equations like con1, con2, con3. It is a constraint 1, constraint 2, constraint 3. You write anything. Whether you use alphabet, you use numerals, no no restrictions on that. Like you can write EQ1, EQ2, EQ3. Well, you can write anything just to, but you must know. It's better that you write some comments so that you understand it what you are writing. What does it mean? Generally, it's the best practice. And this, if you see this one, con1 dash dash, this is syntax. It is needed. It means it is the equation that has to be solved. So dot dot has to be there. And x2 minus x3, if you see the problem, this one, x2 minus uh, x3 greater than 0. So here x2 x3 equal to g is for greater. See, this is the syntax you can see here on the side. Both sides equal small e. See it. Yes, another important point is that it is not case sensitive. Whether we write small e or capital E doesn't make any difference. So this is for equal to. For greater than g. For less than, both sides equal, then L. Plus minus is same. Multiplication star. Division slash. Exponent double star. Or you can also write power in bracket. That is also another way to write it. So you write these constraint values. Whatever we function we have, z is equal to square sqr. This is what I'm telling you, that it has that those features available like exponential and all these things. Absolute value you want to calculate. So but these syntax notations you need to search because it may not be clear to you in the very beginning. So once you start solving it for square, what to do? SQR x1. If you do not want to use xq or x1, so you can write x1 star x1. That is also square. Okay. So once you do it, then we have these, first we define equation, then we write these equations. Okay, and then we write objective function, and semicolon is needed at the end. For each and every section, after every section, we need semicolon, that I will let you know. But these are syntaxes that you need to understand. Mostly we use these equal to, greater than, less than, and plus minus is similar, multiplication is similar. Just like normal MATLAB, you will find very similar to that MATLAB. Upper bound and low bound. Like I told you, for example, we need to set a maximum limit of generation, minimum limit of generation. You can do it in this way. You can write it in the form of equation also. So dot up is up for upper value, dot l is for the lower value. Like x1 variable, upper value 5, lower value 4. This is what you can fix up. Okay. So dot l lower bound, dot up upper bound, dot l the level value, meaning put your value up, that is what is the dot l. So it will give you solution in from the dot l. Dot m is the marginal value, what we call marginal price, and or incremental change in that particular variable. So it is generally used for if you see the incremental cost in those who studied economic load dispatch. So we talk about incremental cost. So what is that cost? Because when it comes for the bidding purpose or any other issue, so there we need to find the incremental cost, marginal value. So dot m gives the marginal value straight away. You need not to write a separate code or separate equation for that. By simply writing, if you want, for example, the marginal value of the cost of a generator. So simply write cost dot m. You have PG1, generator 1, generator 2. So you get that cost. So you immediately get, okay, if we want to increase the generation of generator number 2, how much cost it has to incur by simply write dot m only. So it calculates automatically. This model, this is a statement that we need to write. It is used to name our model. Like test is one program name. Okay. All within that slash. All means it is solving all the equation. You can write separate equation also. Like if I want to solve one equation, which equation I want to solve? Simply obj. I can write simply obj in bracket. But then it will solve this one only. It will not solve con 1, con 2, con 3. These are another equations there. These are separate equations. So all means it will solve all the equations which are there in the program. Then we have option limit row, limit column. This is for the limiting purpose where we want to suppress the output while debugging. So this you do not use hardly matters. This is for simplification so that we don't have long output files. So then you write the solve statement. Install, solve, test. Test means your program. Solve this test using NLP, non-linear programming, linear programming, any minimizing Z. What is Z? Z is your objective function. This is what is the statement you need to write. Right? Once it solve it, write it. It will automatically use that solver and give you the solution. So you can have this minimizing this function. This is what is the statement. Solve model name test using solver type. This one. Minimizing, maximizing. There are two ways we do it. Objective variable जो भी आपका है, that you can write Z, cost, whatever you want to write. Okay. And these are solvers. There's another solvers available. This is just few of solvers which I have mentioned here. Linear programming, non-linear programming, mixed integer, MINLP. This would be MINLP. Sorry. Mixed integer is needed, particularly in power system. We need to have mixed integer because we have. If you talk about a unit commitment problem, where generators status also need to be there, which is binary in nature, and we have generation which is continuous. So we need to have a solver which takes into account both of these variables. So we have mixed integer that purpose. Mixed integer nonlinear programming. Relaxed. Are we certain what happens when we use R, it gives certain relaxation. Like if at certain point of time, for example, if total generation is not equal to load, that should be there. That is equality constraint. And if it is, let us put zero point 0.5, something of that sort, or maybe some other voltage variation slightly, it relaxes it. So it is giving you solution close to that. So generally, or maybe a status of units particularly, we fix up some variable of status of where it's on or off. And if you fix this, mi, p, mi, nlp, so unless those units are on or off, it will give you the exact value. But if you use R, so sometime you will find that uh, generators, whether they are switched on or switched off, despite that, they are going to give you certain values. So it will not give you the exact unit commitment solution, but relaxed solution where we find that some other units can also, give some power at certain point of time where they should be off in actual. So it is giving you relaxation to the boundaries conditions particularly. This is how your uh, output file look like. Right. I will demonstrate and then it will be clear because it's not clear to you here. This is the way we write it, and the derivative pool refers to the fact that analytical gradients for the nonlinear models have been generated by the games. Means the file which is there, they let you know that how many equations are there, how many variables are there, non-zero elements are there, how much time it has taken, execution time. So all these features are specified by this. Sometimes you find in papers this much time has been taken for simulation, so you can get it from here. So this time and everything, how many questions, how many variables have been solved. So those sort of information is provided by this, because otherwise you need to count. It directly gives you how many variable you are used. Objective value, it is going to specify. We will see it. Then this is how the equation: lower level value dot lo dot l dot up dot m, which we dot m, this is a marginal value. If we talk about this one, this is the marginal value. So this is basically a multiplier. Those who have studied about this, bidding strategies, they understand that a particular generator, if they want to bid in the market, they decide it on the basis of the marginal value, because they wanted to know that how much cost is involved to generate the next unit of power. So if it is 10 rupees, so they will bid for 12 or 15 rupees. They cannot bid it at 8 rupees, otherwise they will be lost. But how do they know that how much is the cost? So they get it from the marginal value. Okay, how much cost is take involved in generation the next unit. So we can directly get it. So we need to write it separately. That is what I mean to say. This example, now I will not take up this example. Let's go to straight away to the GAMS environment, and then it will be clear to you. This is one basic problem, simplest problem that I have picked because it's easy to understand for the power system problem for people. Minimizing this cost. We have this ABC cost coefficients. PI is the generation by different units, fine. And here, what is important is that I have taken only the PI. I have not taken into the time. I can also have PI comma T. One unit at one time, second time, third time, fourth time, second unit at different time. So that can be done. That I will show you in programs. So this is the way you can write. But for simplicity, I kept it without time only. Let's keep it like this. Subject to the condition, total generation should be equal to demand plus loss. Loss, if you calculate, fine. Otherwise, in power flow, automatically it will take care. And second constraint that we have, that total generation should not be greater than maximum or less than minimum. That is what is the load dispatch problem that we have, and we need to minimize the cost and those conditions. Now, how do we write code? This is what we discussed earlier. First is the set. We need to define the set. Generating units. I already defined set I. How many units? That I will specify. I will show you how to do that. If you are taking time, take time also. So this is the way you can define. Like in some of the problems, a generating unit of this company, the company is also a set. Company A, B, C. Generating unit of company A, first unit, second unit, third unit. So different sets can be there. Time can also be there. So you can have number of sets defined in a problem. Then we have the parameters. Now parameters are the given values like ABC coefficients. They are given to you. Demand should also be given to you. Then also you will be able to solve. Generation limits should also be given to you. Fine. So these are the given values. The demand हाँ हाँ yes 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 or no demand cannot be a set. Yes, what we can do is we can scatter this demand. See what happens when we say why we are making generators. Total demand of the system. When we solve it, it will be solved. It will be solved based on the power flow constraints within the power flow constraints. At which bus that demand is, it will automatically pick it up. You can pick it up. See that program I will show you separately. So what we do there is, but demand is given. Whenever we solve a load dispatch problem or power flow study, demand is given. Unless we do not know the demand, how can we solve it? But generation is to be decided. Fine. That is why it is taken as set, and we cannot take it as a set. Okay, it is given already. So whichever is given, yeah, it should be known that is a parameter. Then comes the variable. So real power generation P, that is the only variable here, along with the cost. And I am taking this problem only, simplest one, right? So the cost is a variable; it is going to vary, and at the same time, your real power generation is also a variable. Next step is to define the equations. You define, name the equation, any equations, equation 1, equation 2, equation 3, equation 4, how many equations are there, you write those. Then you write those equations. Here, first this equation, and here constraints also. You can write in the form of equation also, upper bound, lower bound can also be given. That both way, you can do both ways. Then you write this solve statement. First model, that is skipped. Model, and then model solve all, where we write the all. Yes, that part is this one. Test model, name of the program, and all. That will solve all the equations. After you write this model, then you have this solve statement. Fine, and you can pick up any solver if, like generally linear programming, non-linear programming, if it is not going to solve by that, it will ask for that, and then you can display the results. Now what is important in this case is that we can interface with the MATLAB. So I will show you that MATLAB part later, but let's go back to the coding part first. Right? So how to call these functions from the MATLAB? What we do is we write program in the GAMS. We will not specify the data there. We will write code in the MATLAB, and data will be available in the MATLAB only. A simple command in MATLAB is needed, which will pick up the data from the MATLAB. It will solve in the GAMS and will give back to the MATLAB. And then here we need to interchange these files for interfacing purpose. So that is a simple procedure given on the internet, that how do you interface a GAMS software with the MATLAB software. So two files need to be exchanged, and in latest version I think it is automatically updated. There is no need to interface. the later versions which are there, or updated games. So you can directly write those commands and it will automatically run it. Otherwise, if you see the older versions of the MATLAB and games, there you need to interchange two files of MATLAB with games and games of MATLAB. And by simply doing that, setting a path, and it is going to interface it. Now let us take this. This is symbol for games. This symbol. If you see it, if you open this game, this looks like this, and I can open a new program just like any other software. And if we write, star, this is for the comment purpose only. I can simply write ELD program, enter it again. You can write these. This is the way it is writing comments only. Fine. So once you do it, the next step is, we'll go back to this one. We need to define the set. So you define set. Capital small hardly matter. I told you it's not case sensitive. Set I. Any set I. Okay. And this is the way it. We need to enter data within these bracket like slashes. Like if there are, let us put 3 units. So I will write 1, 2, 3 units. Or another way of writing this is that I can write 1*3 *3. Because there are 30 units, so you can write 1, 2, 3, 4 up to this. So this is one. This is the way we need to write. Okay. So once you write these sets, just for separation, I again write a comment. Let us find it, separate it out. The next part is your parameters. Parameters. Okay. So in parameter, what we do? Parameters. If you write parameters, see, this is what again. If you parameters, so you need to write parameter with any of the parameter again. Like I need to write a. Now, for example, this is a, and I need to write AI. Why AI? Because A is for different units. So I will write it cost coefficient. I will specify the data within this. One space. For the first unit, let us suppose it is 100, comma, 2 space 200, comma, 3 space 300. So there is 1 space, 2 space hardly matters. You don't have to bother about that. Okay. Another way of writing this is, now AI, then I can write BI. The capital is there hardly. I told you it's not case sensitive. Again, you can write cost coefficient similarly. Now, 1 space 10, enter. 2 space 15, enter. 3 space. The difference in A and B is that either you can write here, then you need to write comma. If you go to next line, there is no need to write to comma. So you can write in both way. Fine. So ABC, if you write one, whatever value you put up, that is for first unit, the second I, third I. Okay. Similarly, I can have CI cost coefficient unless you write this, slash, it will pick previous one, it will pick up as, yeah, take it as comments only, the cost coefficient. So again, you can write 1 space 0.001, 1, comma 2 space 0.05, comma 3 space 0.8. This is how you can specify ABC. What else is there? P demand, PD. This is your demand. You can specify, for example, it is 300 megawatt or any other units. Anything else we have? We can also specify Pmax, Pmax I. This is also a way to write max unit value for each unit. So I can write again maximum generation limit. One specifies 200, comma second unit is, let us suppose, 150, comma third unit is 100. As you can write, you can write in very similar way P min also. Let it be 20, 15, and 10. These are the parameters. Anything else we have in our problem? So then you write semicolon. In set also we write semicolon. After every keyword, these are keyword. Set is keyword, parameter is keyword, variable is keyword. Fine. Once you do it, then again, just for separation, you can write a comment. Okay. Next, what I need to define now? Variables. Okay. So you define a variable. Variables. It's better to write variables. Otherwise, what you can do is, for example, variable cost, comma variable t. This is the way you can write. Or if you write variables, then there is no need to write this variable with each and every variable, and it is the best practice, rather good practice, because you have number of variables, so it is not advisable to write with each and every. And once you have this cost and this, you can define it. And if you come to know that now I need to have another variables, so whenever you know it, you write it down in between. For example, if I need to add introduce A, B, C, D, E, F coefficients also, add them, hardly matters. Now what is next is equations. Equations, you define equations. I OBJ is one equation. OBJ is objective. You can write anything, it's not fixed. Then you can write EQ1. I prefer this EQ1 so that it's understood first equation. Then you can have EQ2. Like if this is, if you let us suppose this is demand power balance, you can write comments with that also. Okay. Now here when we write equations, the certain equation will be there which is dependent upon certain variables. So that I will let you know. So like if it depends upon I, so I can write within bracket equation 1 bracket I. So once we write the equations, we can introduce it later. And let us write another equation, EQ3 And let's stop it here. Mm, Once we write these equations, now we need to write the equations. One define equation first, then you write equations. You have first equation is objective. Objective dot dot. This is the syntax. Okay. So objective dot dot. Now what is the objective is cost. See this function simple cost. Fine. Summation I vary from 1 to n. So I can write cost equal to E. This is the way it need to be written. Cost is equal to. Okay, this is syntax we already have studied there earlier. Uh, sum sum of all the units. Sum bracket I. Sum of all the I. Comma. Okay. Ai plus bi star p bracket I. Ai plus bpi plus pi star pi star. You need to multiply two times. Okay. And you close the bracket and semicolon with each equation. So summation of all this ai bi pi. First equation. Then you write eq1 dot dot. What was the next equation? PD is equal to the PDAP generation. It can be written on either side. Is equal to sum I comma P bracket I. Sum of the generation. Loss, for example, forget about loss right now. You can calculate it in load flow study. It will automatically, because I haven't included the power flow constraints there. It's simply load dispatch problem. So there is no constraints as for line limits and voltage limits are concerned. Next is EQ2 dot dot. I want P min I. Minimum should be less than greater. Minimum value of the P min I should be less than the PI. Okay. Similarly, I can write for maximum as equation number 3. P max, we need to write exactly the same. P max, P min, whatever it is written. It P max should be uh, greater than the PI. Now, one thing is to be noted here. If you see these equations 2 and 3, on left hand side and right hand side, they are dependent upon I. So I need to include that I in the equation. Equation 2I. It can be time dependent also sometimes. So this becomes T. So when you define equations in defining equation, there also you need to include I. Two is 2 and 3 only. If you do not do it, it will tell you This is what you need to do. It will point out at that point only. We will take intentionally introduce some error, and then we'll see that how to find out that. This is the condition. What else is anything needed? I think this is what we have. Then we have model statement. Model. Now we need to save it. Uh, right now it is untitled underscore one, so I can save it. For example, let's save it. Save as, you can save anywhere. For example, test, keep it test only. Model test slash all. Okay, model statement. Now what is needed? Next, solve statement. Solve what? Test. Name of the program. Using this, you can write down, note it down somewhere. This one. Solve model name using solver name, minimizing that function. So test, sorry, solve test using LP, for example, linear programming, minimizing cost. Okay. And the last you can have display. Display, you can write cost dot L, cost dot L, cost dot M, cost dot UP, cost dot LO, whatever you want, you can do it, comma P dot L. Okay. So once you solve it, then this is the command here for running purpose. This one, yeah, you run it. It says, if you see, this is the file, that LST file. I told you LST file. Error message is there. Just see error message. Endogenous operator not allowed in linear models. Means you can use LP. When you solve it to be optimal solution. If you see on this side, this is the solution. This is the cost here we are getting. Now we have displayed it. You displayed it here. This is the cost 4955. Generation first unit 200, 90, 10. 300 on the basis of its cost. Now if you go up here, you can write this equation of objective. At each and every step, how it is calculated, it will show you these values: upper low values, lower value, marginal value, for different equations. So what I mean to say is that there is a complete, history of the solution available. You can find it out. Sometimes it will lead to infeasible solution. So if you want to see infeasible, so you go to the solve equation, you will find that equation number 1 is not feasible. For example, if both generation is not able to meet the load, so it will show you infeasible solution there. And now, for example, I intentionally do this. Now it is giving some error. Let's see what is the error. So once you see the error, it shows here symbol neither initiated nor assigned 141. Now you can see this star here, 4 stars. This is the error message 141. This is here. You will find it. There is some symbol nor and then neither started nor assigned. So you need to read this error here, what it means, and accordingly change it. That means that if you see question number 3 and equation number 3 that we have defined is different and there is no symbol defined. It is not dependent upon units I. So we need to include that I. So it is point. You just need to read this LST file only. Wherever there are 4 stars, that means it's error. But the error is there only. If you see the solve statement and display, they by default has some. They will show the error automatically if there is error somewhere else. And if you remove this, solve it again, you can get a solution. Now, what is important in this case is that there is a possibility it can be interfaced with. What I need to do is there are two statements: lib include dollar lib include metout lib include metout cost dot l lib include metout p dot l and p depends upon I. These are the two whichever variable you want to get displayed in MATLAB, you can write that in a sequence. I will show you some program and that will be clear. And then come to MATLAB environment. Here, this is one command that we need to write, gams underscore output standard. This is for standard output only. If you don't write, hardly make any difference. But this is the command that it will you will be available in many of the programs. Gams underscore output is equal to std, standard output. So it will show you the complete values. Now, just like your MATLAB program, I need to write cost and p, two variables that were there, which I showed you here, that this is what we need to display in MATLAB. So I write cost p gams and the name of the program I need to write it is test. Now it is also important that you save this program in the same directory where there is that MATLAB program also. So I can save it. It's in hybrid model. So I know where my program is. So I am saving it in this because it is under this folder. So I have saved it here. So now if I run it, I get these results here. These results are displayed here. Fine. Now we can have load flow programs also. Load flow program that I will demonstrate one program. So what I mean is once we have this, so you can have these in variable. We can find this p. So that is easier to work in MATLAB. This you already must have done, if not now. So like if I wish to plot it, so I can plot it generation of different units like this, and then you can cut paste it accordingly. Generation. So this figure you can define the axis on x side, y on the side, and similarly there are many more data that can be easily worked in MATLAB environment. So it gives you an ease that the data can be transferred easily. Now I'm just going through very fast now. Now there is one way. This is what we have done. Load dispatch problem. Data has been given in GAMS itself. Another ways, because here we are not considering that where are the generators, at which bus they are. So it becomes difficult because the problem of research is not of this type. Problem of research generally will have to be tested on a standard system where we have, you know, real power limit, reactive power limits. Then we have, you know, voltage limits, line flows, ambient ratings, everything. So that data needs to be specified. That can be done in GAMS also, but it becomes tedious to solve it there. So what we do is that we keep data in MATLAB, bring that data in GAMS environment, and then run it. So we will not give any data in the GAMS. So I'll just show you the program, and then it will be, I think it should be clear to you. If you see this program, this one here, I am specifying this nodes and branches. Nodes, that is standard system. Then we have LES statement. आप उसको छोड़ दो. This is for J and J1, they are can have similar values. If J is varying up to 30, so J1 will also vary up to 30. Parameters. So this is what we have defined parameters. PG max, PG minimum, PG max 1, QG, P demand, Q demand, whatever variables you have, you define them. Sorry, parameter, you define them. But parameter value will not be specified here. They will be given in MATLAB. Variables you define, just like your normal program. Upper bound, lower bound, you can specify here also. Equations we have defined. All these equations, equation 1, 2, 3, 4, 5, depends upon your program, which problem you have picked up. This was the simplest problem that we did. It can have big problem. Number of constraints can be there in a system. These are some normal program that we have. Now this is what we need to understand. Here these are line flows equations. Here we need to use that incidence matrix, and these equations can be used normal sending end power, receiving end power, real power, reactive power, and this is how we can be. This is a programming part, but we are doing like cost function limits. Like these limits are specified. You can see the limits here. In very similar way, you need to specify. And here also model statement, solve statement. Then you need to write this that lib include matout command so that it takes it to MATLAB. Fine. And display. So that is why I told you it's flexible. Display, it can be written later on, it can be written before and also. Okay. So this is one program on which I have done where data is not specified here. Now where is the data now? Now you go to MATLAB. This is a MATLAB environment. This is the data that I have specified. This you must have seen, or it is available in Hadi Sadat book or anywhere in Mat Power also. We have 24 bus system because you can see 24 here. And we define like first column specifies your bus number, second your voltage, angle, third your generation. This is the way you can specify all these. Line data, like line 1 connected to 2. This is first is R, X, shunt. This is 1.75 is the MVA limit. Line data. Just like if you studied that, if you're not studied, to just for the sake of idea only, you can take up some problem from Hadi Sadat or Mat Power. Small problems on load flow that will make you understand how to take the data. This is how we specify the data in MATLAB. Now, we also need to write that in this case, which particular column is specifying R, which is specifying X of a line. So for that, we write a separate function. Like if you see this particular command, PG min bus 5, fifth column, means in matrix bus, fifth column is your PG minimum. Here, bus 10 means 10th column in bus matrix will be your QG max. This is how you need to specify it. And these values of QG max, I am writing here as output. And if you see these variables, these parameters, they are the same parameters which we have specified here. In PG max, PG minimum, PG, they must be specified. It means whenever GAMS is as solving any problem, whatever parameters are there, its value should come from the MATLAB. So in MATLAB, I need to tell very clearly that which column is which particular parameter. Once you define it, then it is ready to solve. Now, another simple uh, function that we need to use is the Y-bus. Y-bus formulation has to be there because then only it solves it. Okay? It has to be there. So this is standard program. You can get it if you. I can give you my ID. I can share it with you also. So there is no need to change the Y-bus program. It's a simple program as it is. Data you specified. The data how to make GAMS understand that which particular column is of particular parameter that you specify in the function. So if you see this data bus and line, we have taken two matrices, bus matrix and line matrix. From these matrices only, it will specify that first is your demand, second is your voltage limit, MVA limit, all these things can be done. And then we have this small program. Don't go into don't be bothered about this is a large thing written. It's not needed. It's simply commands only here. This is one simple command where we can get the file. It will call the ask the file which data is to be picked. So I can pick up that data where I have specified. Here the same command data file which I just show you that because it also need to be because it's a MATLAB now. It has to be in sequence. So data is the function here. It will pick up the data file from there. Then if you see the next, it is Y bus also. It is Y bus for data, then Y bus. After that, ABC coefficient, all these things that you can be written. These are F print. They are for printing purpose only. GAMS and output standard. This is what I wrote last program and I showed. This was standard output only. And here, the program that I have written, this one, GAMS. This is the name of the project. Your program there in GAMS environment. In GAMS environment, I have written two programs here. This is project underscore CG2. If you see the program name here, project underscore CG2. So the same program has to be written in this way. If you see here, I would cost P GAMS test. So I have solved test, the economic load dispatch problem. So I have simply written the name of the program. Similar way you need to write. You can directly write it here. And then you can specify this PG max, PG minimum, all these input variables, input parameter rather I should say. And here on this side it is the output. And these input should be in the, all these input parameters are, if you note it down, PG max 1, PG min, PG maximum, they are all value the parameters here in the same sequence. And if you see the display here, whatever we have displayed here, PGN, PQGN, the same will be on the output side here. So input parameter will be specified on this side, output on this side. Rest it is simply for displaying purpose. Baki whatever we are writing downward, it's not a part of the program. This is the only command that you need to write. Just like the command that we have written, we did in MATLAB earlier. This one simply. But the only thing was that we need to pick up the data. We need to use the Y bus and then use this command. So that is what is done there, and it has been written in such a way that I get line flows from which line to which line. That so once I solve it, it will ask for the file from where to pick the data, because there is one initial two commands are for picking up the file only. Get file. I pick up this file because the data is here. That too I show you the data. To pick up the data, there are two programs here basically. So again, it is going to compile, and you find that this is the result shown here in the MATLAB environment. You can display also. Fine. So once you do this, rest variables in the workspace. Now you can plot whatever you want to plot. Another important point in this case is that how to find out whether solution is feasible or not. So what we do is, there are some files metdata.gdx to metsol.gm. These files need to be copied, and this is one small thing that you need to learn. In document there is one GAMS directory. Automatically it will form when the moment you install the software. GAMS directory will be created. In GAMS directory you need to copy these files in program, because whatever solution we have obtained in MATLAB, that data need to be transferred to the GAMS environment now. In GAMS directory we need to put that data after solution. Once we do that, now your GAMS program can run. Now you run because there is no data specified, but now we have put up the data after solving it in the MATLAB, because MATLAB solved it by calling GAMS. Now we need to put it back in the GAMS directory and then solve it. Now if it gives you optimal solution, it means your program is right. If it gives infeasible solution, means it is solving but solution is not feasible. So that is what we need to see. It means the solution what we have proposed, yeah, program it is running perfectly. Got it? So what problem with the problem that we were discussing, that we can always have that, fact devices included in this. We just need to have the mathematical equations for the fact any fact device. What's your TCPAR, StatCom, UPFC, SSSC, whatever it is. You just need to write mathematical equations, and we need to specify, the power balance equations and the power injection equation. Include those equations there only. Specify at which bus it is there, and once you solve it, that what reactive power which is being supplied by that will be automatically taken care in the load flow program, and you can get the solution. And in fact it can also contribute to the cost, because the moment it changes the P, it changes the cost also. So whatever is your objective function, accordingly it will give you the solution. So I think though for many of you, because unless you do it yourself, it's slightly difficult to understand, but at least this GAMS program which I have shown you, economic load dispatch problem, that you can solve. And particularly for MATLAB interfacing, there is resources available on internet also. You simply type GAMS interfacing with MATLAB, or simply download that software also. So GAMS website is there. So the link will give you, I think, student version up to 30 or 50 variables. So that is sufficient for you, because there are no, I think we are solving 2 variables only. So 30 variables is large. So it will solve, take care of your problem. So MATLAB Simulink can also be included. That is the addition that they have done. And in fact, fuzzy and all these things also are also being, taken care by the GAMS now, up in the latest version that is there. So this will make again very comprehensive tool to solve the problems. So I think I would like to stop here. So if you have any query, any doubt, please, you are most welcome to ask.
Hello.
Yeah,
Hello. And that you're applying this. Suppose you can apply the genetic algorithm or any differential algorithm. You also can solve that economic load dispatch problem. What is the difference between this? Hello.
Yeah, it's not audible actually. Yeah, difference between G and
Genetic algorithm or differential evolution, anything can apply and find out the economic load dispatch problem. But is there any advantage of that? What are the you are explaining this programming? What is the difference? That
yeah.
also you can, that also you can solve by using some
See,
modern.
you can use those tools, the genetic algorithm and other programs, but The problem with those tools are that you need to use, you need to have good programming skill in that. It is very simple. Yeah. You need not to use the solver. Obviously, the functions are available for G and PSO also, but still, student find some difficulty. And it is up to it is it's a choice. The GAMS is your it's deterministic. It uses deterministic techniques. It doesn't use probabilistic technique like GA and PSO. So that is the difference between the two. GA and PSO, and cloneme optimization, they are probabilistic techniques. They give different solutions. It gives you same solution every time. That is what is the difference between the two. Rest it is up to you, and it is very easy to program. What I am telling you, it gives you flexibility that you write equation number one first, equation number 10 later. So whether you write, any of the equation anywhere. So there is no such restrictions. But in MATLAB, you need to be very specified. It is case sensitive also. GAMS is not case sensitive, and moreover, it provides interfacing with MATLAB, Simulink, and all these things. So that is advantage with the GAMS. Data can be easily transferred to the GAMS and from MATLAB, and MATLAB can also transfer to the GAMS. So this is what is the advantage with this. Rest it is the choice of the people that whether they want to go for PSO and GA. It's up to you.
Okay.
Any other query? So next call is Maharashtra. So do you have any query? Any Siddhartha College?
Sure, fine, fine. Thank you very much. I think it would have been better that in case you had laptop and
Full explanation.
because what happens when I used to attend, so most of the time we give in on PPT form, so that was very difficult to understand. So once you solve it and you get a feel, and these, but you need to have a software. Otherwise, many of the files, if you want to get some files, you can have my mail ID and you just let me know. The certain programs, like in fact, I can share some programs with you. Fine. So for others also, basic programs can be given. So you can have, but there are tutorials available. You just go to the tutorials, you get an idea about this, and then you apply it. GA can be. Hmm. Easily. Huh. Yes. That can be done. Exactly. You just need to, write the function on which criteria you're going to fix the location. The moment you know that, that yes. Loss minimization kar lo, that is fine. You place it, you get losses at different positions, and you get that. And voltage sensitivity can also be done. There's so many ways to have that. That can be done. That can be done. Sure. I think there are some work I can you can maybe with Dr. Sri Sharma, my guide. So the students have worked on certain areas, and one of my students also working on locations placement. So, so that I can share, no problem. That will because you get an idea, so it's better. There's certain work already being done. Why to waste time in that? Just move ahead of that. That should be the purpose. So I'm very open to this. I'm not secretive in that matter because, and it needs to be there. Then only we can promote it. Yeah. Thank you. Sure, ma'am. Sure. बंद हो गया ना एक मिनट पहले
लीडर चंडीगढ़
हम गए
आई
जी।
we thank Dr. Vaiti Sharma
मैं तो
for the
मीटर में सर
guidance
निकल रहा हूँ,
and
बस आ ही रहा
because
हूँ।
of the
हाँ
detailed explanation that he has given.
चलो चलो
There
पिक
are
कर लो,
lot
फिर मैं
of
कुछ 10
alternative
मिनट में आता हूँ।
methods for finding the optimization
हाँ
techniques.
पिक कर लो
And we
सर।
thank you. And there is a lunch break and we should be back at 2:15. Thank you.
चलो
Thank you very much. Thank you so much.
चलो, नो आई कैन डिस्कनेक्ट है।
यहाँ है तो उनको बोलो हेलो 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 सिस्टम माइक यूज हो रहा है हेलो 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 किसी का माइक उठा रहा है उसको उठा ही नहीं हेलो हेलो आप इस पे कर दो वेबिनार
Okay, I can see a room full of empty chairs. Mm-hmm. Mm-hmm. Ah, okay, perfect. Okay. Yes, yes. So you see some software with some network with the relays. Yeah, perfect. Perfect. Okay. So now it's going. Now everybody sees this. And then if I click again, yes, okay. Can you see my yes. Okay, I see where this is. Oh, this is the entire screen. Yeah. Hmm. Okay, perfect. Okay, this is working. So when should we start? 10 minutes. Okay. Okay, perfect. Thank you. Okay. Okay. Bye bye.
A ne, još. Rekao sam, kako je, zubiru, ali sad može tako. Da je drugi rimoni neko, koja će ima to?
Ja, neku javnu prezentaciju. A sam
Hvala.
ne, neki hangout.
Još ima to izvini. Znači, koliko mi neobično kad kažeš mulim, ti kao mulim pričaš da maznem, a ja mulim...
Da udarim.
Pa ne da udariš, ne da uglaviš, da muliš. Ne, sam jednu zastavicu. Gledam drugu zastavicu do kako ćemo ona vrata tamo.
Čekajte, ja vam desno uperam.
A to i ja tražim. A sad će vedno. Pa treba uskoro da pravimo ovo i zaratimo ovo. Da sad će da bude to. Prvi zima. Jedini koji je prelako
Vi su naši nešto gore. Još tražim.
Evo ti urke.
Ja, kam? To je tebi.
Našao.
Ne, uspravno neki vedimo. Dajmo ako možemo. Idemo prvi biti. Stavite.
Okay.
Yes, ma'am.
A very good afternoon to one and all. And Chandigarh.
No, you can. Mic off किया था.
A very good afternoon to all the participants at NITA Chandigarh and all the other nodal centers. So we have with us our expert Rados Petrovic. He's a business developer of Typhoon HIL and he has joined us from Switzerland. So we are really blessed and we are really enthusiastic to have you, sir. So we are ready here to listen to you. So I'll just tell about this course. This is a short-term course through ICT. In the sense, we have around 7 centers throughout India from different states like we have Tamil Nadu, Maharashtra, Rajasthan, Gujarat and Madhya Pradesh. So from many states, many institutes and universities have joined us for this course. Around 7 centers we have and all the participants at all these centers are faculties from different engineering and polytechnic colleges. So, and we have participants here at our center, NITR, and we have our MTech students, those who are working in the area of power systems. So, I think this will be a very useful lecture for them. And I will hand over the session to Rados. Thank you, sir.
Thank you very much. Thank you for your introduction. So I'll do my best to be brief, precise, and not to speak too fast. It was brought to my attention that sometimes I tend to speak too fast. So I hope you can see my screen now. Yeah, I can see that you can. So it's a pleasure to meet all of you. It's a wonderful auditorium and really a great event that you're organizing and hosting. So it is a pleasure to be here, to attend. Mentioned, I will try to introduce and speak a little bit about some of the latest technologies that are available and that are being used in different parts of the world to help with some emerging issues that we have with the increasing dynamics of the new grid. So with these power electronics enabled power systems, where we have a variety of different sources connected in different ways, on-grid, off-grid regimes, and what are the challenges that we are facing with these changes and how we are addressing them. So this is the short agenda for today's webinar. So this introduction is going to be very fast, just a couple of minutes, and then I'll focus more on some of the experiences that we came across when it comes to the new power systems. So about new challenges, some solutions that are proven to work, and I will share with you some of the experience of our customers. Then very briefly, I will introduce our company, who we are, how we started doing what we do. And then we'll go through a couple of demos. I will show you how some of our tools are working. Then we will have a special treat for all the attendees of the seminar. We are going to give special access to our software tools, special trial, if you may, for all attendees. Mr. Rajesh Moria, that is also there with you, is going to give you the credentials at the end that you can access our software, download free of charge, and share among your auditoriums and students to spread this technology a little bit. And that's it. And then finally, we can have a short questions and answer sessions if there are any questions at the end, and if the auditorium is awake at the end. So because this is in total 1.5 hours. So if needed, we can also make a short break, maybe between the presentation and demonstrations, a couple of minutes to stretch legs, and then we can continue to the demos. Also, I would encourage everyone to stop me at any point if there are some meaningful questions that you would like to discuss. Then we can also do that. So that's it. So I would start. So as mentioned, as you saw from the topic, so we are going to speak closely about protection, about new fax devices, about distributed generation, hybrid systems, both terrestrial and offshore, and how all this is impacting our existing infrastructure of the grid. So here comes this title. The new grid is all about software, meaning that in difference to the old grid that we had for about a century, this good old Nikola Tesla invented transmission of electrical energy over long distances with zero losses. Nothing pretty much changed in the power systems until, let's say, 10 or 20 years ago, when we started adding these renewable sources to the grid, to different points of the grid, mostly the distribution layer. And then also these energy storage fields, where we now have combinations of conventional and alternative sources operating closely in some isolated parts of the grid. What happened here? Well, basically, all these converters that are connecting renewable sources or storage facilities to the grid are power electronics converters that are operated by some form of software. And then on top of this, we have communication layers, which are again new layers of software. So in difference to the old grid, we can say that now this grid is quite complex when it comes, because we added layers and layers of code and software to it. Similar things happened to automotive industries about 20 years ago. This is why now we have about 80 microprocessors in every car. What this means, wherever we have software, there are potential failures, potential bugs that can ruin the stability of our network, and all this software has to be tested. And the questions are how we can deal with these software issues, how we can test our software, how we can commission this software before we are actually letting it work in the real power system, in the real environment. So these are just some of the challenges that we are facing. It's nothing strange to say that performing tests on megawatt equipment in labs is not really such a pleasant thing to do. It doesn't scale easily. Our tests are not repeatable. We cannot automate the test processes. It's dangerous. It's endangering people's lives. So the question was whether there are some new technologies that can help us deal with these issues, that can help us bulletproof our equipment and harness the potential of software and complex control fully, so that all our life can be easier, so that we can scale up or multiply the number of operating points and tests that we can cover, so that we can bulletproof our equipment against particular grid codes. And this is it. So the question is whether we are having some tools that can help us test our equipment for any kind of disturbance, for any kind of fault, for any kind of shoot through, faulty switch, for anything, any scenario possible that we can think of before it actually happens. And of course, is it possible to automate these testing processes? You are probably all familiar with this big trend of let's say, new generation of grid codes that any distributed resource in the grid or that any protection device has to comply with or comply against. So these new emerging grid codes that are now also not, India is not also stranger to this form, especially with this need or this resolution of your government to install about 200 gigawatt of renewable sources within the next 7 years. All these sources will have to be tested against particular grid codes that are becoming more and more complex by day. We are speaking about tests like low voltage write-through, frequency write-through, anti-islanding operations. So all these tests are extremely hard to perform in labs, especially when we speak about megawatt labs. The answer was to see whether there is some technology that can help us deal with all these issues. We are also speaking a lot with some of India's prestigious institutions like CPRI along these lines to see how this equipment is going to help include all these distributed generation to the Indian grid. So when we speak about some traditional methodologies, this is a very simplified presentation. We are all familiar with the different simulation tools that we are using on everyday basis. MATLAB probably being the one most common, most familiar, and the one that probably every single attendee now to this presentation has spent some time with. What was problem with simulation is that the results are not that true, because not only that we are simulating the power part, we are also simulating all the control software and all the control system, which makes our results not as real. On the other hand, it was very nice cost-wise. It was very easy to work in simulations because cost is low. You can simulate anything that can cross your mind. Just problem was the results were not that good. And on the other hand, we had tests in the full power labs, or for example, in some power hill configurations where we are not testing, we are not performing any kind of simulation. We are still using power. So we are testing equipment with full power. The problem here was, of course, it's extremely costly. It's dangerous. It's slow. We can cover maybe 5, 6, 10 operating points per day, not more than that. But of course, on the other hand, the results were very good because we were testing the real stuff with real power. But the question was, is there something in between that can provide us with great results, but also with some ease of use, something that can scale, something that doesn't include power, so that we can automate the testing processes, perform regression tests, etc. And the answer was yes. Now with new technologies that we have, with new computational platforms that we have today, we are able to simulate the power, to make a digital twin of a network or of a power stage of any kind, and simulate it in such a manner that the actual control system can be connected to the virtualized power stage. This means that we can now use very fast computational platforms to solve some very complex equations that are describing particular systems, and we can interface real control, real protection devices, real facts devices, all these smart layers, all these software layers of the network, and we can interface them to a completely digitalized power stage. This concept is now known as controller hill. How this looks, basically everything that has power is simulated with specialized computers, and then everything that is executing some form of control algorithms, being in protection devices or converter control, is being interfaced directly with these specialized simulators. If you want to see how this looks in real life, these are just some examples. What you can see on the left are some snapshots from labs in Schneider Electric and ABB. Schneider Electric also in Bangalore is probably one of the biggest customers or biggest users of this technology in India. So this is how it looks in real life. So actual control systems, actual protection devices, all of these can be connected to these kind of boxes that are then, we can call them even specialized computers or supercomputers designed to only do this to simulate the behavior of power system entirely. So this is how it looks in real life. Now this is of course only on the converter level. This is how the technology started, because you know, if we speak about dynamics and comparing power systems dynamics to the, for example, converter level dynamics, we know that converters are switching on very high frequencies, which then demand very small simulation time steps on which this computer have to perform. So the biggest demand was exactly on the converter level. Then now we are expanding to the microgrid level and power system levels by adding some slower dynamics on top of this. So if we speak about the power system testing requirements to perform something like this, then we speak about a combination of different simulation platforms that are executing different parts of this model on different time steps. For example, for most of the power system simulation, we are completely happy with simulation time steps of, for example, 10 microsecond or maybe 20 microsecond, depends on the level of detail we need. But in order to connect real control of a genset, of a diesel generator, or of a solar inverter or an active filter, then we need to embed the real controllers. To connect them to this kind of simulation, these parts of the network that are being, let's say, controlled by real controllers have to be simulated in much smaller time step with much bigger dynamics. So some of the specs, if we speak about what would be the ideal test bed that could fulfill these kind of requirements, that can be used both for AC and DC distribution systems, that can let's say perform on different execution rates, to also at the same time read PWM signals that are switching with, I don't know, 100 or 200 kilohertz for active filters, for example, and then also simulate another part to simulate a large network without overkilling our resources, and then also simulate communication protocols, synchronize with the GPS signals, embed real protection devices to the setup. These are some of the specs that this setup would have to comply with. So if you speak about timescales of interest in new power systems, we can see that now we have a really large span, starting from the microsecond level or even nanosecond level for sampling of the PWMs in the inverter switching. And then we go more and more to some hourly changes or daily changes when it comes to, I don't know, movements of sun or discharging the batteries, some shaded curves, fuel cell dynamics, and etc. So all of these time scales have to be, let's say, satisfied by the same very setup or same very test bed that we are using for our tests. And of course, just to briefly summarize what are the benefits, I'm not going to speak too much about this, and this slide speaks pretty much about itself. I mean, just to justify the need, why are we again searching for such alternative approach to dealing with our with the emerging issues of the new grid? Well, I mean, if we can avoid going to the lab by any chance and spending time with spending, you know, megawatts of power and kilowatts of power to perform some tests, this means high maintenance cost, high cost per operating point, very slow processes, and something that we cannot automate or perform well. So this is the idea. Now this technology that we are speaking about has entered different fields. Not only the terrestrial microgrids and power system, power electronic applications are now depending on this technology. We see the great applications also with marine applications, some offshore platforms, so oil and gas, which is again energy. And then in transportation, where we have hybrid propulsions or traction applications, hybrid electric vehicles, microgrids of fast chargers, etc. So all of these fields are now being covered by or answered with the same technology that we are going to show more about later on. So just a couple of examples. This is one of the major, let's say, heavy-duty hybrid vehicle manufacturers, Liebherr. This is a German company. So this is an example of application of such a technology for hybrid propulsion, combination of diesel and electric motors. Then one very interesting use case. Sometimes the most trivial things are the hardest one to deal with. So we recently had some experience with Statoil and Shell, who are pumping the gas, or actually, let's say, transmitting the electrical energy from the very north of Europe to the south. Their biggest issue was that during the winter months, the transmission lines are going north-south, and the wind is blowing east-west. And where we have strong wind, the lines get connected, they trip, and then the system needs weeks and even months to, let's say days and weeks to reboot and restart. So the greatest issue for them was to bulletproof the turbines, so the whole system can reboot itself fast and automatically, so they don't have to send experts to the field, spending tens of thousands of euros or hundred thousands of euros to reboot the system. So what you can see on the picture is the testing facility in ABB in Switzerland. Here on the picture we have two LCI drives, 20 megawatt each, back to back, being tested in the lab. So this is the lab when they were testing the software that is driving these two machines. So 50 megawatt altogether to test software. So this was before they learned about the technology that they use today. So we were able to replace all this lab infrastructure with one of these boxes right here. So what you can see on these pictures is completely original control system that was driving this drive right here, now being tested on one of these boxes. So the completely 50 megawatt setup is simulated with this box, and then the original control system for the complete setup is tested here. So we're going to speak about more use cases later on. This is just to conclude this part of the presentation. What you can see on the picture also here is that this technology also found its place in the academic circles. This is one of the first hill-based teaching laboratories ever made by Professor Kushik Rajashekara, who is your countryman. Probably a lot of people there know Professor Raja. So he was one of the first to harness this technology for teaching purposes. What you can see here is a completely hill-based teaching facility that he established in 2012, so 5 years ago. Many more places like this now exist in the world because not only that this technology can help with actual tests, it is a very interesting tool and let's say easy to use tool, easy to spread when it comes to the teaching activities and research. So today Typhoon has aside from a growing number of let's say commercial businesses that are using this technology, we have also a very good relationship with a number of academic institutes worldwide, but also in India. We introduced ourselves in India for the first time, I think, last year. Since then, quite few academic institutes have joined or acquired this technology for their own internal purposes. These are just some, few of them. NIT Srinagar also ordered a couple of days ago one of their first hill units, NIT Uttarakhand, and more are coming, of course. So this is just a partial list. You can find actual testimonials on our website, sharing of different experiences, etc. Also very important for you as academics is that this technology is very well accepted by IEEE community. There is a growing list of papers published in the IEEE Explorer that you can find. There's more than 60 papers already published, developed solely and entirely in this environment that we are going to show in a couple of minutes. And just a few cases. This was one of the latest setups that we delivered to US Energy Department. What you can see here is a hybrid generation, so distributed generation testbed with, let's say, simulated network of, let's say, a couple of tens of buses, where we have different generators, different machines, some of them controlled externally, some of them simulated in some lower level of detail, active filter controller, the real one, connected to the setup, and some solar controllers connected to the setup. So this is one of the, let's say, most advanced microgrid test beds that exist in the world at the moment. Of course, it can be much larger in scale. This is just a short example. Yes, was that some question?
No, sir, there is no question. You can continue.
Okay, I thought I heard something. Okay, thank you very much. So just to describe what was in this particular testbed, these were some of the requirements specified by the US Department of Energy. So this is what was covered with this kind of setup. Of course, all this equipment can scale to very large applications depending on the need. Then active filters, something also that is very close to the protection, to the, let's say, the energy efficiency field. What you can see on the picture is active filter office of Schneider Electric in Oregon, USA. You know, it was very hard for people to believe at first that this technology can actually work. So what you can see here on the picture in the corner is how this commissioning process actually looks like. So, you know, the active filters are especially interesting, or they are especially demanding when it comes to the dynamics. So these are the converters that are switching on very high frequencies. So for people that are dealing with active filters, it's they kind of got used to doing everything in the little lab, you know, step by step, because there are not too many tools that can help them with what they do. So you can understand that there was a certain disbelief that this new technology can also work for them. So what you can see here is actually first attempt to connect the system, first trial. So this is why you see forest of wires when engineers were connecting, you know, line by line, piece by piece, and testing their control systems. Also another example, integration of 8 megawatt battery storage facility in South California, Edison. These, what you can see on the picture, are ABB control systems being tested on one of these boxes. This is also why this is very interesting for battery storage application, is that you know, batteries are probably the easiest to ruin during the tests. You just, you know, charge them a little bit over the limit, or you discharge them a little bit too much, then you ruin them, and they're extremely expensive. So for 8 megawatt grid battery facility, it was essential to simulate the batteries and validate the control without using actual batteries for this application. And etc. This is just also to show that more and more of the relevant facilities are accepting this technology, not only for testing today, but also as a part of the certification process. One of the first institutes that is pre-certifying the equipment against these very complex grid codes like BDW was AIT in Vienna, and now we are expecting that CPRI is going to be the first one in India that is going to certify renewable sources or these converters with this kind of technology that we have here today. So this was this introductory part, a little bit about the challenges, a little bit about what are the possible solutions, about new methodologies that we have today, as thanks to some enabling technologies from the market and some use cases. Then I will spend a couple of minutes just to present the company very briefly, so that you know who we are, what we do, and why are we doing this. And then we will switch to the demonstrations. Between these two parts, I would like to offer at least a 5-minute break because paying attention for more than 45 minutes in a row is quite problematic. So after the presentation of the company, I suggest a 5-minute break, and then we can go to the demonstrations. So let's go through this part. As I mentioned, we are a relatively young company, started only, let's say, 9 years ago. But if we consider that the people who started the company were people in the field, spending years in ABB and some DMS companies, we can say that the need for this kind of tools or the idea for this kind of products emerged from the industrial needs much before this. So the director of our board is Mr. Ray Stetta. He's also the sole investor who backed our company. Probably this name would be familiar to you as a founder of the company Analog Devices. So a lot of you are familiar with the Analog Devices equipment. Yeah, and I can see that you're laughing to this picture of this building. This building is actually a donation from Ray Stata to MIT. This is Ray and Maria Stata Research Center. They donated the building to support the research activities of MIT. You can see that it's very unconventional design, to say the least. So 3 main offices of our company, one being in MIT in Massachusetts, and then 2 more, one in Baden in Switzerland. We also have an office in Technopark Zurich, and a strong development center in Novi Sad in Serbia, where most of our engineering takes part. So these are the founders, as I mentioned, but more importantly, I would say that people faces are not that important in this presentation. I just want to mention that a couple of years ago, actually, sharply 2 years ago, this technology that we are speaking about was recognized by one of the international survey companies called Frost & Sullivan. There is a very interesting report that you can find on their website and also on ours about, you know, comparing some of the different technologies on the market that are dealing with these issues. And that's it. A couple of years ago, the same team that started Typhoon Hill was awarded with the same prize for the medium voltage drive ACS 2000 that you are probably familiar with. So this is the founding team of Typhoon Hill. And then a little bit about the technology was covered in 3 different market research reports in 2015. I won't go too much in detail about this. So this is only for those of you who are interested to learn more about this field. All of this information is available on our website. So what is specific about our product offerings, something that was different before and after Typhoon Hill, our systems were the first one to be offered as a completely integrated package, meaning that all the hardware and software and all the tools that are needed to perform these kind of activities are coming from one company, not from multiple vendors, so through turnkey solutions. And then for those of you, this is probably the most common question that we are getting from time to time is which kind of tool is suiting for which kind of application. So this is just to show what are the most common applications where this technology found its place. Again, something that maybe is interesting only to a part of you to see what are the technology bottlenecks when it comes to different applications and which kind of system is best suiting for which kind of demand. So these kind of systems that we are speaking about can at the moment perform or let's say deal with networks that are let's say up to 16 100 three-phase bus complex. So this is the maximum size of the grid that we can deal with at the moment. And that was this part. So before the demonstration, I would just like to point out a few useful links on our website that might be of interest. So let me just open the website. So a lot of this information and a lot of very nice recorded demos and different webinars are available on our website. I will just point a few links for those of you who are interested to learn more. So the typhoonhill.com, you can find, for example, some nice recordings of this microgrid testbed that we were speaking about. So much more details about what is inside, how it's interfacing with protection devices. And here on this page, you can see even the link to the video recording of this setup that I was showing, how it works on large scale, how we are applying different disturbances, some transients, follow different things. So all of this is available on the website. So I'm not going to spend too much time or waste your time on this, since you can see this all yourself. Then another part that might be interesting for you is under this My Typhoon and then webinar section. Here you can find a number of recorded webinars about application of this technology in different fields, from grid code compliance like SunSpec, or pre-certification of smart inverters, some energy presentations coming from the military perspective in the US, then et cetera. So you can find a lot of these webinars right here. And also, if you're interested to learn more about different experiences from different users, there is this area under company and customers where you can find some, let's say, first phase quotes, experiences, etc. About what this technology can do. If you are interested to learn more about this, so these are just some of the institutes that we are working with. You can download the complete list of published papers right here, or watch some additional tutorials, see how different schools worldwide are applying this technology. As I mentioned, a list of published papers. All of this is available on the website, so feel free to browse a little bit, download, or even ask some of these materials directly from us. We are happy to share them at any point. So this would be it. Madam, please let me know if you think now it's a good time for a 5 or 10 minute break before we continue. So for the people to relax, is this a common practice? So as far as yeah, please.
Yes, sir, we can have a 5 minutes break, I think. And again, after 5 minutes, we will just start.
Okay, perfect. So stretch your legs and then we can start after 5 minutes with going through some demos.
Yeah.
Thank you very much.
Yeah, now it's 3:05. We will start at 3:10.
Okay, perfect.
Okay, sir. Thank you, sir.
Mm-hmm. Hmm?
फेस मैम कर लीजिए
सर ये तो मैम को भी दे देना, शी इज अ पार्टिसिपेंट. So I think all the centers are listening here. I would like to like inform you something like this Typhoon HIL, their representative is here with us, and I have given the coordinator's name as well as the email, phone number and email ID. So they have the software free of cost. They have the CD. So they will be sending the CD to all the centers. This software is a free software that which sir will be explaining to you now. Next session will be the demonstration of that software. So that software is a free software, and that will be given to you. By mail. That will be sent. That is a CD will be sent to you through mail. So I've just given the coordinator's email ID as well as the phone number. Might be he will contact you and he will be mailing you this. Not mailing, as in he will be sending you the CD. And they have also a WhatsApp group, I think, where they have all the webinars and everything will be there. So I'll just tell them to add your center also inside this WhatsApp. So you will get all the updates of this software as well as hardware. So all the nodal centers, around 7 centers what we have, I have just given the representative your address and everything. They will be sending you the details. So this was a small information which I would like to share to you. And after 5 minutes, we will have a sales session.
चलो आप यहाँ बैठ जाओ, वो खाली पड़ी है चेयर्स में, तो इसलिए कह रही हूँ.
Yes, I think our break is over. 5 minutes have passed.
Yes, sir, we can start now.
Okay, thank you very much. So before we continue, I would just like to add a comment to the statement that the software is free. It's not that the software is free. We are giving it away for free, meaning this is a significant part of our product when it comes to the commercial, let's say, accounts. But because for us, academic network is very important. We see academic institutes as strong partners in bringing new technologies to the field. This is why we want to use this opportunity to open this software to all your partners, to all your institutes, to all your students, free of cost, so they can get familiar with the technology, but more importantly, to influence the further development of the technology in the following time. So for us, this is a gesture of goodwill that and we would like to encourage all of you to download this software, to play with it, to go through the examples. We have a local partner from Quarbs in Kanpur. Representative is right there with the madam, as madam mentioned. They can, give you more direct coordinates how to download the software and use it. And then that's it. I will show you a little bit how all this works. And then if any questions you may have, we can discuss these things at the end. So share my screen. So what you can see now is the home screen of our software toolchain. So this is everything that I will do now, today, you will also be able to do yourself when you download the software. So I'm not going to show you anything other than what you can do. So for anything other complex things or anything that is requiring some piece of hardware, this won't be shown today. For this, you have a lot of demos available also on our website. So for me, it's more important to show you how you can start with this software, how you can start using this, how you can browse through examples. This is the highlight of the today's presentation. So what you will notice from the first moment you install and start this software is that it's very clean. We are doing our best to only add the things that make sense and that people are using. So this software and the hardware that is running along with it is made ground up for power applications. So you won't find anything else in this tool other than elements needed for power applications, whether these are power electronics, power systems, something applied to the marine applications, large system, small system, and everything you will find in here is made ground up for this application. If we are comparing to MATLAB, this is like MATLAB designed for power engineers. When I say this, this means that every element in the library on the left is designed for power electronics and power system engineers. What makes this approach so great or so easy to use is that modeling of networks does not require any deep understanding of any programming language. So designing circuits like this, what you can see here is IEEE defined 30-node feeder with some substations, some measurements on every bus, then some transformers, underground cables, transmission lines. What you will find first is that customization of this kind of model, of building this kind of model, requires only knowledge of electrical domain, meaning every model is parameterized by its technical spec. So 0 equations. So for a transmission line, you can choose which kind of model you like, whether it's RL coupled or PI, number of phases, 2, 3, 4, model definition, and etc. So nothing complex. You need some converter topology. This is how you model converters in Typhoon Hill. Just drag and drop them. That's it. If you want this converter to be controlled externally by a real controller, you just choose which control signal you want to use to drive which switch inside the converter. If you want to control it internally, then you say internal modulator, and then just define the switching frequency, that time, etc. So all the modeling, everything is done completely with your mouse. So no need for writing equations. And then this applies for anything that you can find in this library. Some usual libraries that you came across with in MATLAB, like this mathematical operators, discrete functions, custom C blocks, it's all here as well. Additionally, we have libraries of very specialized elements like different IEEE defined exciters, some steam turbines, governors, etc. So the library is very rich, I would say. It's also constantly growing. We have 4 updates of software every year. So major updates that are bringing some new models, some new features, etc. And all these updates are influenced and driven by the market. So when I said at the beginning that we invite you and encourage you to use this software and give us some feedback, this is what we mean. Feel free to join our groups on LinkedIn, on our website, our blogs, and write comments, suggest changes and updates, etc. This is as far as the library is concerned. When you download the software, you will also download the complete documentation with it. So if you are wondering what kind of element you can find in the library, there is this Typhoon Hill schematic editor library document that you can open and find this detailed description about everything in our system. Solver logic, hardware information, but also information about any model that is inside the library. For example, you are interested how a particular machine is implemented, you will find the equations of the machine, complete subsystems and everything. So that's it. So I'm not going to go too much through the library because you can download this document yourself and see everything you're interested in inside here. And then the level of complexity of the system completely depends on you. Everything can be modeled with small detail if you don't need something specific, or you can go to very detailed models like, let's see. For example, this relay right here is modeled right now in our circuit, in our system. If you go in the layer beneath, you can see how this model with how this relay is implemented with 4 protection functions. Every one of these blocks you can go beneath and you can see how the actual logic of this system is implemented. But what is the most important part, I would say, of all, is that once you're done building these kind of models, compiling this and executing in a form of simulation is just one click away. So the system is going to recognize what kind of circuit you are building, how you are organizing the circuit, which Hill device, which hardware device you want to use at the end for this model, and it will compile for a particular hardware device from the scratch. Right now, we are set to use the smallest device that we have, this 402 Hill. This is the entry-level device that we have. And although we are going to run this model in offline regime, it's going to be compiled for a particular Hill device so that you can switch to real time just by plugging in the USB cable. Compilation lasts less than a minute. And then let's see what we are compiling. So we are compiling this IEEE defined 30-node feeder. We are going to run this model now in offline regime to see how this works and to see how accurate our models are. So this is one of the models that is defined by IEEE community to serve as a testing model to test and verify the accuracy of your simulation platform. So our models are in less than 1% error, which is quite precise. IEEE is allowing 5%. So the model is done. The system will automatically going to switch us to the next step called control panel, where we can set the sources, play with frequencies, change any parameter of the circuit, and do all this while the simulations are running. And then interfacing to the real hardware device, as I mentioned, is just plugging in the USB cable. So my PC is a bit slow, so don't mind this. So there we go. The model is done. But the software is asking you now is that it cannot find any hardware device connected to the PC. This is going to happen to you also because you don't have any Hill devices. So what it's offering is to load the model to the virtual device. This is an offline simulation mode where we are simulating the behavior of the Hill device on our PC processor. Again, this is completely hidden from the user. So if you noticed, we haven't done anything to, I don't know, to deal with the compilation process. It was completely automated, just one click and everything is here. The same compilation process is when you use hardware devices, it's completely the same. If you go back here and you take a look at the compiler log, you will see that this model, this whole network is going to run with a time step of 8 microseconds on the 402 device. And you can see how much of the 402 device resources would be utilized for this model. So let's go here. We can load the settings. Every example in our system comes with the predefined settings, which include, I don't know, the setting of sources. So this is the grid voltage, the grid frequency, etc. And of course, every one of these models that we are running is coming with the UI file. This is like a user interface file that you can run to play with your models. So this is this one example, a very simple one, easily recognizable. Now, as a next step, I would also like to quickly show you how this looks on some different examples. For example, a battery storage inverter working in the grid connected mode. And in this example, we are going to run the converter with the control that we also designed in our system. And then we are going to start injecting some harmonics, injecting some different grid faults to the system. Just stop the simulation. And then play with this circuit for a while so that you can see what kind of tests can be performed easily. Finally, after this demo, I will going to show you another example of let's say, offshore microgrid. This is going to be a ship. You can see the propulsion of the ship here with the induction machine model, some models of different models of the load, etc. But first, this is the model that we are going to run now. This is a battery storage converter. So you can see here the battery model, again, that is coming as a part of the library. You can see that as all other models, this one is also customized only through the technical spec. So even for battery models, we have some predefined battery types, nominal voltages, etc. So this is how we are designing the curves of the battery. This converter is going to be controlled through internal modulator. Just a second for the model to load. So this converter is going to be controlled through internal modulator through this control algorithm, which is a closed loop control. And the switching frequency for this converter is going to be 10 kilohertz. So in order to run the model, and this is one of the examples that are coming with the installation of the software, so you can run it yourself. I'm just going to open the custom UI, meaning the interface file that you can also, again, design yourself. We have a built-in scope that we can use to observe the grid voltages and the currents of the converter. And then we can start playing with the system. For example, add harmonics to the network. Then you see how your converter is going to behave with a particular harmonics injected to the network. You can optimize the filters, etc. Switch back to the nominal grid, unbalance the grid. So any kind of test that you can think of can be easily executed, implemented here. On the back of every one of these buttons, if you double click, you will find Python code. So this is open source programming environment for those who are really advanced and would like to spend, to do some more advanced things here, like test automation and working on automated test scripts. this is all available here. Of course, all these harmonics changes, the unbalanced grid, all this can be done even manually. You don't have to build these kind of interfaces, although they are built quite easily. All of these operations can be performed again with your mouse click. For example, you want to simulate a broken switch inside the converter. There you go. One of the switches is now not conducting. And then you can see how this is influencing the grid, etc. So these are some simple examples, the most basic ones. When you download the software and you open the schematic editor and click open, you will find yourself in this folder, where you will find a lot of examples in power system domain, in power electronics domain, in microgrids, in hardware in the loop, meaning embedded external controllers that you can run from the scratch and play with. So if we open power electronics, you can see this battery storage example that we are running right now. There's some simpler ones like boost closed loop, and then some induction machine, open loop, etc. So feel free to experiment. Feel free to browse through the examples, play with the software, join our LinkedIn group, and see how useful or not useful you find this in your regular teaching activities. Then one more example that I would like to show you is this marine example. So this is, as I said, a power stage of a ship, where we have some diesel generator, some generator measurements that we have right here. So power measurement layer, propulsion with induction machine that is connected to the machine shipboard through the three-phase inverter that we are again controlling with the control algorithm designed in the same environment. Here we have some battery storage facility that is again controlled internally, and then some auxiliary loads here. So the complete shipboard power management system that again can run, this kind of model can run even on our entry-level devices with a very small time step. Again, compiling this model and running is just one click of a button, and you will see now the compiler log compiling this model for the HIL 402 for an entry-level device. So what you will get from our partners right there, from Mr. Rajesh Moria, who is sitting with Madam right now, until this model compiles, I can show you where you can download the software. Just open the browser. So if we again go to our website, there is a part on the right called My Typhoon. Then there is a place where you can, where it says login. So when you go to login, you are immediately transferred to the subscription page. I will log out so you can see how this works. So you're going to find yourself on a window like this. Then you can sign up right here and use activation key to register that Mr. Rajesh Moria is going to provide you with. So this is going to be a fully blown software environment with all the toolboxes and everything included to your license. So it's not just a free trial copy, it's a full-blown software that you can use. So the model is almost done. While we are waiting for the model, if you have any questions, feel free to ask also now. There we go. So the complete ship power stage is going to again run with the time step of 1 microsecond. even on our smallest device, on this 402. Just for the comparison purposes, for those of you who are dealing in power systems, our entry-level devices, this KIL 402, can simulate roughly a network of 83-phase buses with all the loads and switches and everything, with time step of 10 microseconds. The simulation was running, so this is why. Okay, I'll load the model. There we go. So there we go. Now we are in the shipboard power management system, running the simulations. You can start the propulsion. You can see the power. You can go to the layers below. This is a battery storage measurement facility, generator facility. So all of these propulsion facility and all the measurements. And here command to start and stop the propulsion in this custom UI that we build ourselves. Again, the scope is there. You can choose which signal you want to observe on which channel of the scope, and all these advanced functions that you would have on any other scope, like observing digital signals or capturing. Let's say we want to capture all this data that we are dealing with. We can force the trigger. Say we captured all the signals. We can zoom in to really large detail. This is 2 megapoint capture function, so that we can export to some, let's say, to MATLAB or some other software that you would like to use for some kind of analysis. So all this is inside. So I wouldn't go in too much detail. I would prefer to make it more of a discussion now. So I'm opening the stage for any questions that you may have, because all this software and all these examples are going to be completely open to you. Just download the software, use the activation key that will be given to you by Mr. Rajesh Moria. And then we invite you to share your feedback, and that's it. Thank you very much for your time, and please do ask anything that you have on your mind.
Any query from any of the nodal center or the participant present here? We'll go one by one. Penalex College, Maharashtra.
No queries, madam.
Now, would you like to give any feedback?
Hello?
Yes, sir.
Yes?
No queries, madam.
Okay, so thank you. IEC College. IEC Group of Institutions, Greater Noida. So do you have any query, or would you like to give any feedback? IEC Group of Institutions. Yes, sir. You're not audible, sir. PVP Siddhartha Institute.
Thank you.
PVP Siddhartha Institute.
No,
Vijayawada.
no queries, madam. Thank you.
Would you like to give any feedback?
No, madam.
CV Raman College. PV Raman College. Is there any feedback?
No, madam, no feedback.
Kanchipuram SC SVMV University. Sir, do you have any query? Hello? Sir, you are not audible.
Hello?
Yes, sir. Yes, sir.
Ma'am, if you are going to use, if you have further any doubts, can we contact them? Is there any mail IDs or through which we can contact them? Because we are going to have that one Typhoon to be software to be given to us. If you have further doubts, how can we contact them?
Sir, I'll
Yes.
share the email ID.
Okay,
I'll share the email ID. You
Yes.
can type your query on that.
sure. Sure, ma'am. That's it.
Yes.
Thank you.
Also on our website, you can find the contact information of our Indian partners.
Okay,
So this is also there. Feel free to contact them for any query.
sure, sir. Thank you.
Thank you very much.
Okay, so on behalf of So that's all for the day, and we'll meet tomorrow at 10 a.m. sharp. Thank you, Mr. Rados, for such a wonderful session. Sir, आपको तो कुछ शेयर नहीं
Yeah,
करना?
sorry. Thank you very much for inviting me, and hope we will have a chance to meet also in person sometime soon.
Thank you. Thanks a lot, sir.
Thank you. Okay. Bye-bye.
Bye, sir.